What if the story that humans tell about the Earth is only the final paragraph of a book that has already occupied billions of pages? What if every monument of concrete and glass, every satellite blinking in low orbit, every library of pixels and paper is, in geological terms, an exclamation mark at the very end of a sentence so long that the letters blur into an indistinguishable smear? The opening idea is a small hammer striking a vast, ancient bell. It reverberates with a single message: Earth did not begin with humans. It is a thought designed to unsettle the comfortable narrative where human beings see themselves as the culmination of an inevitable rise, the apex of evolution's staircase. That image of inevitable ascent is convenient, emotionally resonant, and culturally persuasive. It consoles, it explains, but against the scale of deep time, against the slow, indifferent arithmetic of rocks and oceans. The human story is a recent afterimage. The planet had grown old before it taught itself to remember. To grasp that discomforting fact is to stand at the edge of two kinds of vertigo. One is the temporal, the staggering distance between a human lifetime and the time it takes mountains to be born and worn away. The other is epistemological, the admission that the physical traces of entire epochs, perhaps even the traces of complex, purposeful activity, can vanish almost without a whisper. It is an entrance into humility. It is an invitation to imagination tempered by the sober machinery of geology. Imagine compressing Earth's 4.54 billion years into a single calendar year. In such a year, the first continents assemble like long-delayed tectonic parties in January and February. By March, sunlight finds molecular work to do, coaxing chemistry toward the first murmurs of metabolism. For 11 months, life is microbial, silent, immense, and unimaginably patient. The dinosaurs do not appear until mid-December. By 31 December, in the last hour, the great age of reptiles ends in a catastrophe. Only in the last minute of the final day do anatomically modern humans appear. In the last breath of that minute, civilization arrives. In that compressed view, the human era is a fingerprint on glass, visible yet extraordinarily delicate. The Earth of the Hadean Eon was not benign. It was a planet in violent formation. Molten rock swirled, raindrops were acid, an enormous bombardment played percussion in cosmic rhythm. There was no stable crust for long stretches, only a churning skin of magma and ash. In that furnace, the basic elements found their arrangements. In that chaos, the first tectonic templates that would later host oceans and continents were sketched. The image of a placid blue marble studded with continents is recent. For most of Earth's early chapters, it was a raw and hot thing, an incandescent laboratory. That laboratory yielded not only barren landscapes, but the conditions for chemistry to edge toward life. The Archean and Proterozoic eons read like a slow, patient accumulation of experiments. Microbial mats, communities of microscopic life colonized shorelines, trapping sediment in sticky layers that hardened into the first recognizable fossils. Tiny organisms learned to harvest sunlight, and in the quiet language of molecules, photosynthesis began to push oxygen into the atmosphere. It was not an event so much as a long negotiation. Oxygen was initially poison to the existing microbial communities, and its appearance precipitated one of the earliest major biological revolutions. The great oxidation event rewrote the chemistry of seawater and air. Over millions of years. It prepared, reluctantly, the stage for more complex bodies. For the vast majority of Earth's history, the biosphere was a dim microbial skin. The sudden blossoming of complex multicellular life during the Cambrian period was explosive only by long-term standards. Radiations of form and function filled new ecological spaces. Yet even those flourishing eras were vulnerable to changes in climate, chemistry, and celestial fortunes. Mass extinctions, there were several, wiped the slate clean in geological blinks. The Permian-Triassic extinction, often called the Great Dying, erased well over 90% of marine species and dramatically thinned terrestrial life. These were resets, sometimes rapid, sometimes gradual. They were the ecosystem equivalent of page turns in a book punctuated by unexpected edits. From these cycles of flourishing and purging rose new dominants, reptiles that would become dinosaurs, then the mammals that would quietly, persistently diversify in their shadow. Tectonics continued its slow choreography. Continents collided, split, drifted. Rivers cut canyons, mountains uplifted and collapsed. Glacier and storm and the chemistry of the atmosphere were mop and palette, repainting habitats across eons. The continents themselves were not static platforms upon which life played. They were actors, moving, reshaping the very theaters in which evolution unfolded. Against such mobility in time, the persistence of physical evidence is capricious. Sediments bury and preserve, but plate tectonics recycles crust into the mantle in cycles measured in hundreds of millions of years. Rocks metamorphose under heat and pressure, erasing the original structures and any human-like scratches they might have carried. Chemical weathering strips away fragile materials, wind and water scatter or dissolve them. The planet is both archivist and eraser. Fossils survive under fortunate conditions, a rapid burial, anoxic waters, mineral replacement. Artifacts survive under even more fortuitous circumstances. For the bulk of Earth's history, these favorable settings were rare. Consider, for a thought experiment, the longevity of a typical human artifact. Plastics, so emblematic of modernity, persist on timescales of centuries to millennia in certain conditions, yet they fragment, oxidize, and are incorporated into sediment in ways that render them unrecognizable. Bronze and stone tools can endure longer, but even stone artifacts are subjected to transport, burial, and metamorphism. Structures constructed from organic materials, wood, fiber, textiles are the least likely to survive the deep timeline unless they lie within dry caves or are sealed in peat or permafrost. Even then, entropy is patient. Over millions of years, few traces will remain distinct from the geological background. That knowledge reframes a provocative possibility. If a technologically capable species had arisen tens of millions of years before humans, could its traces persist to be read by a future archaeologist? The hypothetical draws both scientific curiosity and narrative thrill. It is not a claim that such a civilization existed. Rather, it is a question about the durability of intentional marks against the crushing, eroding, and renewing forces of geology and chemistry. The answer is complicated. On the one hand, some markers of large-scale activity, massive mining scars, unusual isotopic ratios, or persistent structural anomalies could, in principle, leave a detectable footprint. On the other hand, the slow alchemy of Earth erases the subtle and absorbs the human scale into the planetary scale noise. This is where the feeling begins to thicken into awe and a little fear. The sense is not of being cheated out of primacy. Rather, it is the recognition of the fragility of human memory. Cities, monuments, entire technological networks are monuments to a species' impression of permanence. They are built to endure perhaps a few centuries, a bice, maybe millennia. In exceptional cases, they are not designed for the battering of tens of millions of years. Plate collisions will tuck them under other rocks. Chemical weathering will redistribute their elements. A future mountain range could form where a metropolis once stood. Civilization, with all its records, could be a palimpsest overwritten by sediment and heat. Yet Earth also keeps its oddities. Deep in strata, isotopic anomalies can whisper of industrial activity. A sudden global shift in sedimentation patterns may reflect a cataclysm. Charcoal layers record widespread fires. Heavy elements concentrated in ways that deviate from natural baselines might hint at large-scale extraction and dispersal. These faint signals are the kinds of things a diligent investigator would look for. The task is one of detective work, and the clues are filtered through a geological sieve whose mesh size only sometimes permits the retention of pattern. There is an emotional cadence in this reflection. Pride gives way to humility, which shades into a tender loneliness. Humans are storytellers, and the human tendency is to privilege the stories one tells about oneself. The mind that can launch instruments to distant planets, that can read genomes and map the deep history of the cosmos, can also fall into a narrative narrowness, equating technological activity with historical significance. But significance is not the same as duration. The Earth's narrative has room for many kinds of actors. Long microbial empires, ephemeral megafauna dynasties, slow tectonic theater companies. By accepting the Earth's quiet prehistory, humans are invited to expand their imagination and to learn a different kind of reverence. Reverence in this context is not piety, but carefulness. It is the recognition that actions conducted at scales of centuries can trigger consequences that echo through millennia. The geological record is full of episodes where life's innovations transform the planet in ways that can be measured even now, oxygenation being one of the most momentous. Humans now possess technologies that alter planetary chemistry and climate at rates too rapid for many species to adapt. In considering deep time, the present becomes a point of potential geologic significance. The very fact that humans could leave a mark that a future stratum might record imposes a responsibility to act with an awareness of those long arcs. The opening also introduces a paradox of intimacy and vastness. From the standpoint of a single human being, the Earth has a texture of immediate sensations, the warmth of sun on skin, The smell of rain, the concrete underfoot, the hum of a city. These are the scales at which lives are lived and meaning is made. From the standpoint of deep time, those sensations are flickers. Yet the flickers matter. They have produced a mind capable of asking the question that opens this statement: did Earth begin with us? The very ability to ask betrays the raw peculiarity of the present. So the story is not merely about diminishment, about humans being small, but about responsibility combined with humility. The awareness of being a recent phenomenon can be energizing. It can provoke stewardship and curiosity rather than resignation. There is also an aesthetic angle. The beauty of geological processes lies in their patience. Mountains wrought by collisions, rivers carving slow signatures, coral reefs building acre by acre, these are testaments to accumulation. The human eye is trained to prize immediacy, a sunrise, the arc of a flight, the crescendo in a symphony. Deep time asks for a different attention, that of slow cultivation. To appreciate it is to learn to read patterns that span orders of magnitude beyond a lifetime. It changes a sense of urgency in decision-making. Actions are no longer merely immediate moral choices. They are gestures that enter a longer history and, perhaps, contribute to the stratigraphy that future beings, human or otherwise, may read. This opening refuses easy endings. It sets a frame. Humanity's epoch is not the center, but a late arriving chapter. The planet's deep past is not a mere prelude, but a succession of complex, often chaotic, and sometimes beautiful episodes. Large-scale processes are both creative and destructive. Life itself has been a persistent, adaptive force across billions of years, and its current expressions are the results of countless contingent turns. The prospect of erased ages or lost intelligences is not central to the claim. Rather, the central claim is simpler and more humbling. The Earth had a long history before humans, and that history continues to shape what is possible now. The tone here is neither nihilistic nor triumphalist. It is reflective. It is the kind of meditation that encourages curiosity and care in equal measure. It invites a viewer to imagine, to ache a little for the fragile transience of monuments, and to wonder at the endurance of geological and biological processes. It also nudges toward a methodological question. How would one look for signs of past complex activity that may have been almost entirely scrubbed away by time? That puzzle is both scientific and philosophical, and it will underpin the inquiry that follows. To end this opening meditation is to leave the viewer in a productive discomfort, the kind that sparks exploration rather than retreat. The planet is older and fuller than the human narrative suggests. That realization can humble and motivate. It can prompt a more patient sense of history, an ethic of stewardship, and a curious, perhaps even playful, scientific imagination about what might yet be found in the strata if one knows how to look for the faint signatures that survive in the geological memory. The bell that rang with the opening question now fades into a solemn reverberation. The Earth's record is partial. Erasures are thorough. Persistence is exceptional. The human story is brief, luminous, and fragile. It is also capable of altering planetary conditions in ways legible to the stratigraphic record. What remains is an invitation to look deeper, to consider how a planet can harbor complexity long before a species names itself as the protagonist, and to begin the careful work of reading the book's earlier pages without assuming they were written for today's eyes. What if one could stand beside a clock that ticked not seconds but eons, and listen as the earliest ticks of the planet's life unspooled? That image, a person, or rather, a perspective, beside a cosmic chronometer, begins not with a landscape, but with a question. How does a world congeal from dust into a living, breathing planet capable of hosting thought? The question loosens the scene from the human scale and throws it into the slow, furnace-hot theater of planetary birth. The story of Earth begins where most stories of things do, in a cloud, a star-forming nebula, once rich with the ashes of earlier suns, folded and contracted under gravity. Like a hand-sifting flour, the collapsing swirl concentrated matter into a bright, impatient center and a thin, dusty disk. This disk was a workshop of collisions, microscopic grains, each born of stellar furnaces, stuck together with electrostatic kisses. Over time, those grains became pebbles. The pebbles became boulders, and through a choreography of gravity and chance, planetesimals gathered until one, favored by a lucky combination of mass and momentum, grew into the young Earth. There is a particular kind of violence in this making. It was not a gentle accretion of well-behaved blocks assembling like bricks. The early Earth was subject to a bombardment that blurred the line between creation and catastrophe. Collisions were frequent and often catastrophic. giant impacts. One of them, the hypothesized moon-forming collision with a Mars-sized body, did not simply add mass, they remelted the planet. For tens or hundreds of millions of years after such events, the surface was a seething, incandescent ocean of magma. It was a world without stable ground, where rock behaved like syrup and the very notion of surface was provisional. Within that magma ocean a crucial operation took place: differentiation. Gravity served as the most unforgiving sorter, tugging the denser elements toward the center and letting the lighter materials rise. Iron and nickel, heavy and metallic, sank, forming an embryonic core. Lighter silicates floated upward and began to cool into a primitive crust. This segregation was more than a chemical footnote. It was the birth of a dynamo. As the metal core convected and rotated, it generated a magnetic field, an invisible, vital shield that would one day preserve atmosphere and life from the ravages of the solar wind. The iron catastrophe was, paradoxically, a creative event, the making of a concealed engine that would sustain surface habitability. Even as the core settled and the crust began to stiffen, the planet exhaled. Volcanoes, fierce, ubiquitous, often submarine-vented gases trapped in the early rock. Water vapor, carbon dioxide, nitrogen, methane, and ammonia poured into the air. This outgassing assembled the first atmosphere, but it was a world far removed from the blue, oxygen-bearing envelope that now seemed so familiar. The primordial air was dense and toxic by modern standards, a steam-thick, greenhouse-laden shroud that kept the still weak young sun's radiation from turning the planet into a frozen cinder. That greenhouse effect was essential. Without it, the faint young sun paradox would have frozen oceans that had not yet formed. Where did Earth get its water? That question sits at the juncture of geochemistry and cosmic delivery. Some of it came from within, from volatile bearing minerals released during differentiation and volcanic outgassing. Some likely arrived later, delivered by icy comets and hydrated asteroids whose trajectories intersected the inner solar system. The record left in isotopic ratios of hydrogen in different reservoirs hints at a mixed origin, a mingling of internal birth and external donation. Either way, as temperatures normalized and the heavy rains began, steam condensed into droplets and the first true oceans pooled in the planet's lower regions, filling basins and carving provisional shorelines. This settling, however, did not render the planet calm. The early solar system was a busy neighborhood. For hundreds of millions of years, impacts continued, some small, many large. The late heavy bombardment, a hypothesized spike in impact frequency roughly 339 billion years ago, would have scoured surfaces and delivered fresh energy and chemistry to the crust and oceans. Each impact was both a creative and destructive hand, capable of fracturing crustal plates, of injecting heat into the crust, of creating transient hydrothermal systems where chemistry could run wild. In the quietness of hindsight, these violent episodes seemed to be opportunities, ephemeral windows when chemistry could reorganize in new directions. The oldest surviving minerals, zircons, speak in a mute but eloquent voice. Tiny and resilient, zircon crystals carry within their isotopic ratios a memory of temperatures and fluids that touched them. Some zircons have been dated to about 4 billion years old, implying that crust and even liquid water may have existed remarkably early, perhaps within a few 100 million years of the planet's formation. Those early zircons are the planet's fossils of circumstance. They do not show life, but they show conditions hospitable to chemistry of the kind that precedes life. In their crystalline lattices, one can glimpse the outline of a world moving from molten chaos to a more steady, if still tumultuous, state. As crust stabilized in patches, the first continents started to test permanence. But continent here is a slippery term. Early landmasses were often small, transient, submerged, and reworked by volcanic and tectonic forces. Yet through time, as heat escaped from Earth's interior and as material reprocessed at plate boundaries and hotspots, the rudiments of stable cratons assembled. These hard, ancient cores would later be the skeleton on which younger rocks accreted. They were also the repositories of chemical processes. Weathering, sedimentation that would, over long stretches, alter the chemistry of surface waters and atmosphere. Two threads braided through these structural changes: heat and chemistry. The mantle, convecting slowly under the tectonic skin, drove the movement of plates. Where plates converged, crust buckled up into mountains and sank into geothermal furnaces. Where they diverged, magma welled to create new seafloor. These processes recycled surface material into the mantle, altering its composition and, eventually, the chemistry of the regolith and oceans above. Weathering on land removed carbon dioxide from the atmosphere, depositing it in sediments. Volcanic eruptions returned carbon to the air. On these long scales, Earth's climate was not stable but dynamic. Push and pull between atmospheric gases, solar input, and geologic feedbacks. The chemistry of the early oceans was a rich palette. Salty, certainly, but chemically diverse in ways that mattered for the origin of life and the future of ecosystems. Hydrothermal vents, chimneys of mineral-rich fluid on the seafloor, offered gradients of temperature, redox potential, and chemistry. Such gradients are not mere curiosities. They provide the disequilibria from which metabolic processes can be powered. In these places, complex organic molecules could assemble and persist long enough to be tested by the blind trial and error of molecular interaction. If life is a solution to a set of chemical problems, how to capture energy, how to reproduce information, then early Earth provided a laboratory with many different benches, cold shorelines, warm tide pools, deep sea vents, and transient lakes. Throughout this unfolding, Earth's atmosphere morphed. It did not do so by gentle editing, but by a sequence of rewrites. The earliest air was dominated by volatiles. Oxygen was almost absent. That absence matters. Oxygen is both creative and corrosive, a powerful oxidant that would, when it became abundant, enable high-energy metabolisms and the construction of complex body plans. But oxygen also corrodes many pre-existing chemistries and structures. The rise of oxygen millions of years later would be a planetary-scale transformation, analogous to a revolution in the economic or social organization of a society. Before that time, oxidizing agents were rare, and life, if it existed, would have been adapted to a world where different energy currencies prevailed. One can imagine the planet's history as a series of thresholds crossed and then recrossed. Temperature thresholds set the line between glaciation and greenhouse. Chemical thresholds altered the solubility of key elements, and mechanical thresholds, such as when rigid plates began to slide past one another, changed the surface dramatically. Each threshold crossing was irreversible in its own span, and yet reversible on longer scales. Ice ages waxed and waned, continents drifted to new latitudes, and mantle plumes rearranged the face of the planet. The cumulative effect was a planet of emergent complexity, a stage where, after several billion years, chemistry had produced not only self-replicating molecules, but entire ecosystems that could modify the planet in return. That reciprocity, the capacity of life to change planetary conditions, was not yet apparent in the earliest eons, but the seeds were present in the quieter, more patient places, the tidal flats, the benthic sediments, the mats of microbial film growing on submerged rocks. Chemical interactions, slowly accumulated effects. When microbes harvested sunlight or metabolism altered chemical gradients, they changed the mineral environment. Where photosynthesis evolved and spread, it began to alter atmospheric gases. These early biospheric experiments, taken in aggregate, were planetary acts. They were small, minute by minute, but over millions of years their cumulative imprint would be enormous. Throughout this deep, slow narrative, a constant hum is the planet's capacity for erasure. The very forces that fashioned the landscape, the crushing, folding, and heating, also obliterate its earlier script. Rocks are rewritten by heat and pressure. Surface features are buried under sediment and magma. Chemical signatures diffuse and dilute. The record that survives is always fragmentary, composed of resistant minerals, anomalous isotopic ratios, and stratigraphic accidents. That fragmentary nature lends a kind of suspense to geological inquiry. The past is not given. It must be reconstructed from traces and absences, from the silences between lines. And yet the fragmentary record can be eloquent. The imprint of differentiation, a metal core, a silicate mantle, a magnetosphere, speaks to processes that set the stage for habitability. The presence of water and the formation of stable basins speak to environments where chemistry could persist. The rhythms of impacts and volcanic activity narrate episodes that alternately scrubbed and enriched the planetary surface. The slow accretion of continents and the circulation of nutrients via weathering and erosion created the scaffolding for ecosystems to arise and diversify. For an observer standing at the close of this vast sequence at the present moment, where a species named Homo sapiens reflects on the ages, there is a haunting duality. On one hand, the planet had already become old before humans arrived, its core already formed, its magnetosphere established, its oceans collected. On the other hand, the planet was still a laboratory, still subject to changes and surprises. The impressive stability that allowed complex life to flourish was not guaranteed. It required a myriad of conditions to align and persist. To feel the emotional contour of this narrative is to experience both awe and precariousness. awe at the improbability of a world maintaining the right mixture of luck and process for billions of years, precariousness, because that very steadiness is fragile in the face of dramatic rewrites, asteroidal impacts, runaway greenhouse effects, or the slow tectonic mechanisms that could bury surface traces. That combination should not be paralyzing. Rather, it should be instructive. It reframes human temporality, the time of cities and technologies, as a flash against the backdrop of patient planetary work. Yet within that flash, humans have the capacity to do things of long consequence, to nudge chemistry, climate, and surface conditions in ways that will echo for geological time. This part of the story, Earth at 4 or 5 billion years, is a meditation on origins without romanticization. It does not indulge in the comforting myth of a gentle creation, nor does it dramatize catastrophe gratuitously. Instead, it tracks a planet as a system of coupled processes: gravitational sorting, thermal convection, chemical exchange, and the intermittent interference of cosmic actors. It offers images that are both precise enough to satisfy scientific curiosity and rich enough to feed imagination: molten seas, sinking metals, smoky atmospheres, the first rains, zircon crystals preserving the whispers of early water, hydrothermal vents steaming in sunless depths. Against that canvas, the human perspective is a late, bright mark. It appears in what, on geological scales, is a mere blink, and yet it is capable of asking the kind of question that opens this exploration, of wondering whether the Earth's memory might hide other complex actors, of recognizing the fragility of artifacts, and of feeling a responsibility to act in ways that honor the planet's long and patient history. The narrative of planetary formation thus becomes more than a catalogue of physical events. It becomes a lens through which to view the human act of remembering and the ethical weight of being able to change a world that has been centuries in the making. This is the planet's middle register, neither the final flourish nor the earliest note, but the deep, resonant chord that allows melody to unfold. It is a story that calls for attention to small things: zircon grains, isotopic signatures, sedimentary bands, and to enormous processes: core formation, mantle convection, the balance of greenhouse gases. It insists on humility, on the recognition that much of the planet's early autobiography is written in faint ink, and that erosion can be both benefactor and censor. It also insists on wonder, in the way random collisions can produce stable conditions, in the way heat and chemistry can bake a stage where life later improvises. If the human impulse is to tell a story where meaning accrues, then Earth's early chapters ask for a different kind of meaning, making one that is patient, empirical, and imaginative in equal measure. The next pages in this unfolding book will consider how the quiet experiments of chemistry and the patient labor of geology prepared niches where complex life could emerge, and how those nascent lives, in turn, began to inscribe new patterns on the world. But for now, the reader is left with the hum of the planet's early machinery, the clang of accretion, the simmer of magma, the settling of iron to the core, and the first cool raindrops that punctuate a story already ancient before humans learned to tell it. What does it mean to be a ruler of a planet when the calendar of that rule is written in millions, not years? The question loosens the familiar idea of dominion, of kings, empires, and monuments, and replaces it with a different metric: biomass, geographic reach, tempo of change, and the capacity to alter the chemistry of oceans and air. In that sense, Earth's history reads as a parade of dominions, each claimed not by a single lineage or a single mind, but by collective life forms whose abundance and activity reshape the planet's surface and atmosphere. Humans are one such late claimant. They are neither the first nor perhaps the most persistent. Before the age of cities, Earth hosted long rains that left sedimentary signatures, chemical legacies, and landscapes that anyone who knows how to read rocks can recognize. For the vast majority of the planet's biography, the rain belonged to the microscopic. Microbes, bacteria, and archaea were not understudies to later life. They were the principal actors for billions of years. To picture their era is to shrink the imagination to an almost invisible scale and then expand it again by volume and time. Oceans and shallow seas became mats and films of microbial life. These mats, like microbial carpets, bound sediment and formed layered structures called stromatolites, which persist as some of the oldest convincingly biological structures in the rock record. The microbial mode of life was architecture and metabolism, writ small but vast in effect. Collectively, microbes held more biomass than any group had a right to on a young planet. They cycled carbon and nitrogen. They mediated mineral precipitation, and in doing so they laid down deposits that a distant future could read. Such microbial dominance was not a passive backdrop. Some microbial communities devised, over eons, a biochemical innovation that would be among the most consequential in Earth history: oxygenic photosynthesis. When cyanobacteria began to split water for electrons, using sunlight to free oxygen from water molecules, they gradually changed the chemistry of the oceans and atmosphere. This change did not occur overnight. For perhaps hundreds of millions of years, oxygen produced near the surface reacted with dissolved iron and other reduced materials, precipitating banded iron formations and keeping the free oxygen locked away. Then, over geological time, oxygen built up in the atmosphere in what geologists call the Great Oxidation Event. That planetary conversion was a kind of global governance change. An atmosphere that had long favored anaerobic metabolisms became oxidizing, and with that came both catastrophe and possibility. Oxygen was poisonous to many existing organisms, but it also enabled new forms of metabolism that could extract much more energy, and energy is the currency of complexity. The image that helps here is counterintuitive. Microbial rule was, in effect, planetary management. Cyanobacteria and their successors reorganized chemical reservoirs, influenced climate via greenhouse gas modulation, and built mineral archives. They were the first empire builders in the sense that their influence extended across oceans and persisted across eons. To the modern mind, dominance often evokes size and visibility: giant trunks of redwoods, herds of elephants, towering mountains of concrete. But in deep time, the most consequential rulers were often invisible, a lesson in humility about the scale at which power can operate. Multicellular bodies eventually emerged from the microbial experiment, and with them came new forms of dominance. The Ediacaran and then the Cambrian explosion introduced a flourish of body plans, sponges, anemone-like creatures, odd fronds, and then, rapidly by geological standards, skeletonizing organisms, arthropods, mollusks, and early chordates. The oceans, which had long been the exclusive theater of life, grew more crowded and structurally complex. Predation appeared as a new ecological force, driving innovations of defense and mobility. Here, dominance began to take on a new texture, not just abundance and geochemical influence, but ecological engineering. Reef builders accumulated carbonate architecture that would become limestone. Grazers and burrowers altered sediment dynamics, and large mobile animals began to etch footprints, literally, into the sedimentary record. As life tentatively climbed ashore, another chapter of dominion began. Plants colonized wet soils and then drier tracts. Their roots stabilized soil. Their leaves changed the albedo of the land. And their biochemical activity altered weathering cycles that pulled carbon out of the atmosphere and sequestered it in biomass. And in coal seams, forests of primitive vascular plants in the Devonian and Carboniferous created ecosystems so different from anything before that, their influence persists in the very shape of later climates. The Carboniferous, in particular, is an evocative case study of planetary-scale engineering by life. Luxuriant swamp forests, made mostly of towering lycopsids and ferns, absorbed carbon and deposited it as peat, which over time and burial became vast coal deposits. Those scenes are the fossilized memory of an era in which plant productivity and burial rates drove a long-term drawdown of atmospheric carbon dioxide, contributing to climatic shifts and to oxygen concentrations that may have been significantly higher than today. That elevated oxygen, the speculative figure often cited for parts of the Carboniferous, is around 30 to 35%, had tangible consequences. Insect respiratory systems rely on passive diffusion of oxygen through tracheal tubes, and higher ambient oxygen enabled larger body sizes. Fossil evidence and physiological inference together suggest a world where dragonfly relatives with 2-foot wingspans patrolled. The swampy skies and arthropods of prodigious scale crept through the undergrowth. The image is almost surreal, an atmosphere thick with oxygen that amplified the metabolisms of small-bodied animals into gigantism. The age of insects in this sense is both ecological and atmospheric. Insects were numerically dominant, ecologically diverse, and capable of behaviors that shaped plant communities through herbivory and pollination-like interactions long before true flowering plants evolved. Their dominance is recorded in cuticle fossils, in trace fossils of trackways, and in the very composition of coal and sedimentary layers. But if plants and insects altered the chemistry of the air and the structure of the land, it was the reptiles, and particularly the dinosaurs, that offer the most cinematic sense of dominance in the public imagination. The Mesozoic era is commonly called the Age of Reptiles, and for good reason. After the Permian-Triassic extinction, which cleared vast ecological space, Archosaurs, the group from which dinosaurs emerged, diversified into an astonishing array of forms. Dinosaurs occupied many ecological niches. Some grazed and browsed as giant sauropods, carrying necks like masts and bodies the size of houses. Others stalked as bipedal theropods, some small and fleet, others terrifyingly large. Still others took to the air as pterosaurs, or returned to the oceans as mosasaurs and plesiosaurs. Seas hosted ichthyosaurs and ammonites. Forests echoed with the calls and rituals of creatures that, while not intelligent in the human sense, were thoroughly adapted to their worlds. Dominance here meant ecological ubiquity. Dinosaurs were planet-wide in the sense that their fossils appear across all continents. They were numerically and biometrically substantial, and their life histories affected vegetation patterns, sediment transport, and predator-prey dynamics. The deposition of dinosaur bones into sedimentary basins, the churning of soils by their movement, and the spread of their nutrient-rich wastes redistributed elements across landscapes. The Mesozoic surface was a theater where reptiles directed, in aggregate, the pacing of ecosystems for about 85 million years, a duration that dwarfs the entire span of human civilization. Yet dominion is never permanent. Mass extinctions, recurrent, arbitrary on human timescales, and reshaping on geological ones, punctuate these reigns. The end, Permian extinction, erased an enormous fraction of species, reordering the deck and paving the way for new groups. The end, Cretaceous event, likely triggered by a bolide impact and exacerbated by volcanic eruptions and climate perturbations, closed the chapter on non-avian dinosaurs and many marine lineages. Each extinction is a reset. It does not erase all evidence of the former rulers, but it alters the distribution of survivors and opens ecological territories for others, mammals among them, to diversify and ascend. That ascent, the Cenozoic age of mammals, is the immediate prelude to the human story. Mammals have been present for millions of years, often small and nocturnal during the Mesozoic shadow of dinosaurs. After the end, Cretaceous clearing, they radiated into many forms, grazers and browsers inhabiting newly available grasslands, arboreal primates exploring complex three-dimensional forests, and marine mammals returning to the seas in the shape of whales and sirenians. Mammalian dominance looks different from microbial or reptilian dominance. It is a story of endothermy, parental care, learning, and, in some lineages, the growth of complex social structures and greater behavioral plasticity. Their ecological influence reshaped plant-animal interactions and nutrient cycles, and their fossil record teeth, bones, coprolites, tells a story of adaptation and spread. Throughout all these eras, two motifs recur and deserve emphasis. First, dominance is often about numbers and rates more than about monumentality. Microbial mats shaped oceans and atmospheres precisely because they were everywhere and multiplied fast enough to alter chemistry at scale. Second, dominion leaves geological fingerprints of varying visibility. Coal seams record carboniferous swamps, chalk and limestone layers speak to vast accumulations of planktonic skeletons, banded. Iron formations record oxygen interacting with dissolved iron. Dinosaur bones and trackways are conspicuous, but they represent a small sample of what once lived. Preservation is a matter of contingency, rapid burial, low oxygen, chemical suitability, and much of what dominated the surface may have vanished entirely into the grind of erosion, metamorphism, and subduction. That contingency has an ethical and epistemological weight. For humans, who are accustomed to reading durability into stone and permanence into written records, the paleontological lesson is sobering. Dominance does not equate to invincibility. The rulers of deep time, whether they were invisible cyanobacteria or thunderous sauropods, could be toppled by alterations in climate, chemistry, sea level, or by chance strikes from space. Human artifacts and institutions are fragile in a similar but distinct way. They are vulnerable to tectonics, to chemical recycling, and to the slow erasure of heat and pressure. Yet the modern human species is unusual in its capacity to intentionally alter planetary systems, a capacity that gives them a kind of dominion that is more durable in some expressions, isotopic signatures, synthetic compounds, and more ephemeral in others, wooden buildings, textiles. There is also a peculiar beauty in recognizing that dominion on Earth has been plural, many-crowned periods, each with its own architecture of life and its own signatures in rock. The strata beneath a walking field may contain vestiges of microbial stromatolites, overlain by sandstones that once sheltered amphibians capped by coal beds from tropical forests, and above that, perhaps, bones of creatures that lived when continents wore different shapes. To read that stacked history is to perceive a series of regimes, each with different logics of success: metabolic innovation, niche exploitation, sheer biomass accumulation, or adaptability to rapid change. Finally, the narrative of past dominions reframes the human moment, not as an inevitable summit, but as a contingent, recent episode. Humans are heirs to a planet fashioned by microbial chemistry, by massive forests that sequestered carbon, by dragons of the sky and leviathans of the sea that once wrote their stories into sediment. In that context, human dominion is both novel and fragile. Novel in the scope and speed at which they can redirect planetary chemistry, fragile because their artifacts and traces must contend with the same geological eraser that removed so much of the past. There is poignancy in this. The species capable of asking whether others had claimed the earth before them must also accept that their own claim may be readable only as faint chemical anomalies in distant strata. This part of the book, then, is a meditation on succession and scale. It asks the listener to measure dominion in more than size and to imagine the rhythms of power that rise and fall on a planet where time's patient. It asks for humility before the idea that life's most consequential agents have often been small and astringent in the public imagination, and for curiosity about how future geologists might reconstruct our age from isotopic quirks and stratigraphic blips. To understand Earth's past rulers is to be reminded that dominance is not destiny, it is a state, maintained by particular constellations of environment, biology, and chance. The planet's long history is a sequence of such constellations, each one a testament to the diversity of ways life can thrive, govern, and then, inevitably, be reshaped. What does it take on a planet-sized scale to turn abundance into absence, to erase, in geological heartbeats, architectures of life that took millions of years to assemble? This question hangs like a cold light over deep time. Earth has not been a steady cradle, but a theater of episodic violence and sweeping loss. At least 5 times in its recorded strata, the biosphere has been pared back almost to its bones. Each extinction removed between roughly 70 and 95% of species, carving away familiar ecosystems and opening a raw map of ecological opportunity. Those wipeouts are not merely catalog entries in a geologist's ledger. They are existential punctuation marks in the planet's story eras, when the rules were rewritten, when the privileged and the abundant were suddenly vulnerable, and when the future was remade from the fragments left behind. The first banishing end, Ordovician 444 million years ago. The earliest of the great die-offs begins with a paradox of cold and water. The Ordovician seas were rich and diverse. Trilobites, brachiopods, early cephalopods, and vast mats of marine life carpeting shallow shells. Then, in a geologic whisper, the climate shifted. Continental drift parked large land masses near the poles. Weathering drew down atmospheric carbon dioxide, and the planet slipped into a profound glaciation. Sea levels fell as water locked itself into ice, and the sprawling shallow marine habitats, those productive, sunlit shells where most Ordovician life thrived, were stripped dry or reduced to narrow refuges. The rock record remembers in blackened shells and abrupt faunal turnovers. Fossils that had been common disappear. Isotopic excursions attest to major carbon cycle perturbations. The first pulse of extinction came with cooling and sea level fall. The second pulse, as meltwaters returned and seas rose, brought anoxic events and chemical chaos. Perhaps 85% of species vanished. The lesson is stark. Life tied closely to habitat area and marginal ecosystems can be extinguished by changes in the physical distribution of water. The survivors were those that could retreat, adapt to lower oxygen, or persist in refugia. The end, Ordovician, was both a contraction and an opening, an ecological sieve that rebalanced marine communities and foreshadowed the fragility of life dependent on continental shells. A fractured transition. Late Devonian, 372-359 million years ago, the late Devonian extinction unfolds less like a single blow, and more like a series of knocks over millions of years. An episodic unwinding of reef-dominated ecosystems. Reefs of stromatoporoids and corals had built complex three-dimensional habitats in shallow seas. In some places, these reef systems collapsed, replaced by black shales that speak of low oxygen basins and stagnating waters. The probable culprits are manifold, widespread anoxia in the oceans, perhaps driven by nutrient influx from expanding terrestrial vegetation, volcanic pulses, or climate-driven circulation changes. The Devonian's ecological drama also includes the terrestrial colonization of plants, rooting soils and altering weathering patterns, so that life on land and in sea became increasingly entangled. The human imagination finds the late Devonian elegiac the image of sprawling reefs suddenly smothered by oxygen-poor waters, of armored fish and trilobites dwindling, and of the first tentative land vertebrates pressing forward into a world of fewer competitors. The interval removed perhaps 70–80% of marine species and reshaped the trajectory of vertebrate evolution, clearing ecological paths that would later be followed by different lineages. The Great Dying, end Permian, 252 million years ago. If any extinction deserves a cinematic epithet, it is the Permian-Triassic boundary, the Great Dying. Here the statistics are savage. As much as 95% of marine species and over 70% of terrestrial vertebrate species were lost. The planet's ecosystem was almost unmade. The causes are complex and poorly forgiving. The enormous Siberian traps flood basalts unleashed massive volumes of lava and, crucially, greenhouse gases. Carbon dioxide and methane flooded the atmosphere, raising global temperatures. Oceans warmed, their capacity to hold oxygen plummeted, and widespread anoxia ensued. The warming and acidification dismantled carbonate platforms, dissolved reefs, and triggered runaway feedbacks. Methane release from destabilized hydrates, massive loss of photosynthetic productivity, and the collapse of food webs. Geologic fingerprints are dramatic. Layers rich in carbon anomalies, spikes in mercury concentrations suggestive of volcanism, pervasive black shales that record oxygen-starved seas. On land, forests burned and soils eroded. The chemistry of soils altered, collapsing the nutrient base. The Great Dying did not merely prune species, it virtually reset ecological complexity. Recovery was slow and halting. It took millions of years for ecosystems to regain the exuberant diversity that preceded it. The aftermath saw opportunistic, sometimes bizarre survivors and the rise of new dominant groups that would shape the Mesozoic world. The opening gambit, end, Triassic 2–1 million years ago. The Triassic-Jurassic extinction is less famous than the Permian or the end Cretaceous, but critical in shaping the age of dinosaurs. Again, voluminous volcanism. The Central Atlantic magmatic province erupted around the time when Pangaea began to fragment. Massive basaltic outpourings, atmospheric greenhouse gas increases, and consequent temperature rises coupled with ocean acidification and anoxia contributed to a protracted extinction interval. Roughly 70–75% of species disappeared, including many archosaur clades and numerous marine invertebrates. The end. Triassic cut away competitors and opened niches that dinosaurs and other groups would exploit. In the ruins of Triassic ecosystems, power relations shifted. The subtle point is that mass extinctions are not exclusively destructive. By erasing incumbents, they create ecological vacancies, where evolutionary experimentation can accelerate. The Jurassic and Cretaceous radiations of dinosaurs and the diversification of marine reptiles are, in part, a consequence of that clearing. A sudden night, end Cretaceous 6 million years ago. Perhaps the most popularly known mass extinction is the Cretaceous Paleogene KPG event that ended the Mesozoic. The signature story, a bolide impact at Chicxulub on the Yucatan Peninsula, carries a clear, dramatic image, an enormous rock delivering a climatic hammer blow. The impact injected dust and aerosols into the atmosphere, triggering an impact winter. Sunlight was blocked, photosynthesis crashed, temperatures plummeted. Shocked quartz, tektites, and a global iridium layer mark the boundary. But this is not the whole story. Many lines of evidence implicate large-scale volcanism in the Deccan Traps as an amplifier. Continuous greenhouse gas emissions, ocean acidification, and prolonged climate perturbation may have primed ecosystems for collapse. Together, these stressors removed roughly 75% of species, including all non-avian dinosaurs, many marine reptiles, and numerous planktonic groups. The immediate aftermath was darkness and decay. Food chains collapsed as phytoplankton and terrestrial green plants suffered. Those lineages that could exploit detrital food webs that burrowed, or that were small-bodied and generalized, had a better chance. Mammals, which had lived in the dinosaur world often in marginal niches, suddenly found ecological opportunities. The end, Cretaceous, is a textbook example of contingency, a singular, catastrophic event combined with other long-term stresses to reshape life dramatically in geological instance. Reading Extinction in Rock and Isotope. Each extinction leaves its own signature in the rocks, abrupt faunal turnover, black shales indicative of anoxia, carbon isotope excursions signaling massive disruptions to the carbon cycle, spikes in elements like iridium or mercury suggesting extraterrestrial input or volcanism, and physical evidence shocked quartz, spherules, ash beds that pinpoints violent episodes. The tempo varies. Some extinctions unfold across hundreds of thousands or millions of years, their cumulative effects snowballing through climatic and biogeochemical feedbacks. Others are nearly instantaneous on geological scales, a cosmic strike followed by rapid die-off. But the record is always biased. The very forces that produce extinction, volcanism, erosion, heat, and pressure also erase evidence. Catastrophic deposits may bury soft-bodied organisms. Subsequent metamorphism may obliterate delicate geochemical anomalies. Paleontologists and geochemists therefore reconstruct events from fragmentary overlapping clues, a chemical spike here, an extinction pulse there, a volcaniclastic blanket in yet another succession. Interpreting cause and effect becomes an exercise in probabilistic inference, informed by models of Earth systems and by analogies with modern processes, aftermaths, windows of opportunity. The grim arithmetic of mass extinction is paradoxically also a creative engine. By clearing ecological incumbents and collapsing complex food webs, extinctions create a suite of newly available niches. Survivors radiate. Adaptive radiation, the rapid diversification of lineages into newly available ecological space, is a recurring pattern in the wake of these crises. The post-Permian world birthed the Mesozoic regimes the post-Cretaceous world allowed mammals to explore larger body sizes, new diets, and complex social behaviors. The end. Ordovician and late Devonian episodes reconfigured marine community structures in ways that would reverberate through subsequent evolutionary pathways. The image is neither deterministic nor comforting. Extinctions do not favor particular forms in a prescriptive sense. Rather, they interrupt existing adaptive landscapes and create new ones where chance, functional innovation, and dispersal opportunities determine trajectories. Novel ecosystems assemble from survivors, immigrants, and tinkered forms. Over millions of years, the biosphere reconstitutes itself, sometimes into configurations unanticipated by the pre-extinction eras. Extinctions as reminders, fragility, scale, and responsibility. There is an emotional and philosophical weight to contemplating mass extinctions. They illustrate how fragile complex systems can be under concerted stress. They also calibrate the human sense of scale. A civilization's several thousand-year narrative is a synaptic flicker against processes that can redistribute planetary chemistry and biological architecture in timeframes both brief and slow. The extinctions teach caution against facile narratives of progress. They show that dominance is conditional and that ecosystems can be abruptly recast by forces beyond the control of any single species. That very realization folds back on the present. Humanity now possesses technologies and a planetary reach that can, in geological terms, rival some processes associated with past mass extinctions. Rapid greenhouse gas emissions, large-scale habitat destruction, ocean deoxygenation, and biogeochemical alteration are not hypothetical. Many are measurable. The paleontological record warns that when forcings exceed certain thresholds, ecosystems can cross tipping points that lead to wholesale reorganization. The ethical implication is not merely about survival, it is about the humility of stewardship. To know that continents have been remade, atmospheres oxygenated and deoxygenated, and biospheres repeatedly paired is to recognize that current actions join a long lineage of planetary impacts, some natural, some anthropogenic. Speculative echoes, the erasure of intelligences. When the conversation wanders into speculative, documentary territory, another unsettling question arises. Could a technologically active species be removed so thoroughly that little of its intent remains for far future readers? Mass extinctions offer a kind of empirical template. A sudden, intense event, bolide impact or flood basalt, that affects global chemistry and reworks sedimentation can bury or destroy artifacts. Over tens of millions of years, tectonics will recycle crustal volumes, weather will dissolve, and organic materials will decay. But not everything vanishes. Isotopic anomalies in carbon, nitrogen, and particular metals can betray episodes of intense, localized processing. Novel synthetic compounds might leave unusual chemical residues, massive landscape alterations, mined basins, unusually homogeneous sedimentary layers, anthropogenic metal distributions could be legible. Extinctions show what disappears quickly and what, through geochemical stubbornness, persists. Yet the most sobering lesson is that many of the world's most consequential actors have left faint traces. Stromatolites, ancient reefs, banded iron formations. These giants of deep time can be read only by those who know the language of isotopes and minerals. A vanished technological species might leave signatures that require a level of interpretive sophistication to spot. The mass extinctions remind the listener that erasure is a real geological habit. Resilience is often about smallness, opportunism, and dispersal. Closing the chapter, continuity in disruption. Mass extinctions are not anomalies that puncture an otherwise stable story. They are woven into the fabric of Earth's history, recurring, decisive, and reformatory. They fell like editing scissors across the manuscript of life, sometimes gentle and indirect, sometimes violent and immediate. Each time, the biosphere's response was to reassemble, to innovate, and to continue, albeit along different trajectories. To inhabit the human present after learning this is to stand at a hinge. The planet will continue to experience thresholds and perturbations. Some will be natural, driven by tectonics, orbital cycles, volcanism, or extraterrestrial impacts. Others will bear the fingerprints of a single species capable of altering atmospheric chemistry at planetary scale. The past's 5 great extinctions provide more than a catalogue of loss. They supply a lens through which to view responsibility, contingency, and the precariousness of dominance. They teach that endings can be beginnings, and that in the strata of loss are the seeds of future life, if there is time and if the survivors carry enough variation to try again. What if the most recent act of Earth's long theater, the sudden bright ascent of one particular primate, was less a single, inevitable crescendo and more an improbable convergence of anatomy, mind, and culture? That question frames the next scene. Homo sapiens, a species whose unmistakable presence in the fossil record is measured in mere hundreds of thousands of years, yet whose consequences ripple through planetary systems in ways that rival much older geological agents. To say that modern humans appear around 300,000 years ago is to speak in a language of bones, teeth, and ancient DNA. It is a statement about anatomy, the vaulted skull, a brain shape and structure that echo the cognitive capacities seen today, jaws that have slimmed as diet and tool use changed. But anatomy is the scaffolding, not the whole edifice. What transforms a lineage into a force capable of reshaping environments and building complex cultures is the interplay between biology and behavior, the emergence of a cognitive niche in which social learning, symbolic thought, and cooperation compound across generations. The early chapters of Homo sapiens' story are porous with uncertainty and charged with conjecture. Archaeologists and geneticists, working like detectives, find fragments of evidence: a flake of worked stone with a precise edge, a bead of pierced shell strung and worn, a hearthstone blackened with ancient smoke. Each fragment is a small, luminous proof that something was happening in human communities beyond mere survival. There is an intimacy in these finds. They suggest curiosity, an urge for making, a concern for memory and identity. These are not the grand monuments of later cities. They are traces of minds learning to tell themselves apart, to mark territory not only with blood and sweat, but with ideas. Tools, perhaps the most visible of cultural fingerprints, tell a story of escalating sophistication. The slow sweep from simple flakes to complex composite tools, hafted points, microblades, bone implements, speaks of a growing sensitivity to materials and mechanics. A stone point set into a wooden shaft is not just an advancement in hunting, it is a social technology. It presumes shared knowledge, where and how to knap, which plant fibers bind best, which wood takes a haft. Tool-making thereby becomes a vehicle for cumulative culture, knowledge that incrementally improves because it is transmitted across generations and preserved beyond individual lifespans. This cumulative process, more than any single genetic mutation, amplifies human capacities. Control of fire is another hinge in this narrative. Fire is an energy technology that rearranges the daily lives of beings. Cooked food is easier to chew and digest, offering more calories with less effort. Fire provides warmth, extends the day into night, and carries symbolic weight in communal life. Around hearths, social bonds could be reinforced. Children and elders could be kept together. Stories could circulate. The human day expanded in the glow of embers, and with that expansion came new opportunities for teaching, for gossip, for the rehearsal of social roles. Fire, then, reshaped bodies and minds by changing dietary ecology, social rhythms, and the very architecture of communal living. Language, an uneasy, tantalizing hypothesis for deep-time inference, operates in the story as both tool and substrate. Language enables the compression and storage of complex social information. Who's a reliable partner? where the best foraging patches are, how to construct a shelter to resist a particular wind. More than that, symbolic language allows abstraction. It permits humans to talk about the past and future, to create shared myths and rituals, to encode rules that enable cooperation beyond close kin. The formation of trust networks across non-kin relationships is central to the species' explosive potential. Where apes rely primarily on immediate reciprocity and kin alliances, humans came to develop extended networks of ritual exchange and reputation, social technologies that scale cooperation into large, flexible groups. The archaeological record hints at the emergence of symbolic thought well before agriculture and cities. Personal adornments, beads, ochre-stained objects, carved figurines appear in the record as signals of identity and membership. Burials with grave goods suggest a concern with personhood beyond death, a nascent metaphysic about existence and memory. Cave paintings, hand stencils, and arranged pigments are not only aesthetic gestures, they are cognitive scaffolds that externalize thought. When humans make marks intended to be read by others across time, they convert the ephemeral into the enduring. These symbolic acts are small but profound shifts. They create a social memory that can outlast any individual and seed cultural traditions. It is tempting to imagine this cultural evolution as a single revolution, a sudden birth of imagination and language. Some scholars have argued for a punctuated cognitive leap. Others favor a gradual accumulation of capacities. The truth may sit in the fertile middle ground. Slow biological and anatomical changes prepared a landscape where cultural experiments could flourish, and once a certain threshold of social complexity was crossed, feedback loops accelerated innovation. Cultural accumulation, in turn, opened new selective environments, shaping behavior and perhaps even catalyzing tiny anatomical shifts. In this interplay, a species learned not only to adapt to the world, but to adapt the world to itself. Population dynamics and migratory restlessness then translated cultural capacities into geographical presence. For tens of thousands of years, small bands of hunter-gatherers radiated out of Africa, following corridors of ice and sea, tracking prey and plants, encountering other hominins and adapting to a bewildering array of climates. Their footprints reached Australia tens of thousands of years ago and, later, the distant continents of the Americas. This spread was not merely physical. It entailed the transplantation of cultural repertoires, toolkits, hunting strategies, ritual practices that could be modified to fit new terrains. Along these migration routes, contact occasionally occurred with other human groups. Exchanges of genes and ideas left faint but detectable traces in genomes. Interbreeding with Neanderthals and Denisovans, for instance, embedded themselves into modern human DNA, a reminder that human emergence did not happen in isolation but in a crowded landscape of related species. As human populations dispersed, so too did their cumulative technologies reshape ecologies. Hunting by organized groups could alter prey populations, deliberate burning of landscapes, an early anthropogenic act altered plant communities and created mosaic habitats that favored certain food resources. The archaeological data increasingly suggests that Homo sapiens was not a passive visitor, but an ecological agent. Footprints on beaches and bone middens, but also clear signs of large-scale landscape management that predate sedentary agriculture. These interventions were often subtle and localized, but repeated and scaled. They could change the distribution of species and the structure of ecosystems. Then came a pivot in the last 12,000 years, farming. Agriculture did not sweep across the world overnight. It arose in multiple places as humans learned to cultivate and domesticate plants and animals. Cereals tamed by careful selection, goats and sheep gradually shaped to human needs, dogs integrated into human economies. These processes reorganized human life around predictable, stored food supplies. Sedentarism followed. Villages became towns, towns became cities. With sedentary life came population density, social stratification, specialization of labor, and the need for new institutions, rules of property, new forms of ritual to bind disparate persons into larger polities, and early bureaucratic systems to manage surplus. The transformation from mobile bands to settled societies is, in geological terms, a sudden flare. Settlement concentrates material culture, pottery, architecture, metallurgy. It produces new kinds of environmental impacts, deforestation for fields and fuel, irrigation altering hydrological regimes, the accumulation of waste in specific loci. The archaeological record from this era becomes dense, legible, and, paradoxically, more vulnerable to future erasure. Stone foundations may endure for millennia, organic structures decompose, but concentrations of heavy metals, isotopic signatures of domesticated diets, and large-scale terracing and irrigation are the beginning of the human technosphere, the suite of artifacts and alterations that will, in time, leave an imprint in the stratigraphic record. Throughout the late Pleistocene and into the Holocene, the tempo of human-induced change increased. Technologies multiplied, social complexity expanded, and with them the ecological footprint. Megafaunal extinctions in many regions coincide, though debates about causality continue with the arrival or expansion of human hunting. The pattern is variable. In some places, climate shifts seem to play the main role. In others, human predation and landscape alteration feature more prominently. Regardless of the proximate causes, the image that emerges is of a species whose novel ways of life, cooperative hunting, use of fire, habitat modification, altered the fortunes of large-bodied animals and reconfigured ecosystems at regional scales. This accelerating agency created new feedbacks. As humans domesticated species, they created co-evolutionary relationships that would transform both human societies and the biology of their domesticates. Wheat's ability to thrive in disturbed soils made it an ally of sedentary agriculture. Sheep and cattle adapted to fenced pastures and selective breeding. Even the microbial world adjusted to new human diets and densities. Human choices now operate not only on visible landscapes, but on invisible ecologies, gut flora, disease vectors, soil microbiomes, creating cascading effects that alter the planet's functioning. The rise of metallurgy, writing, and organized religion further concentrated human capacity to plan and manipulate environments at scale. Metals enabled more effective tools and weapons. Writing allowed the storage of vast administrative information, organized. Religion and ideology could unify large populations under shared narratives. These cultural technologies were instruments of empire and commerce, but they were also accelerants for environmental transformation. Road networks, irrigation, quarrying on unprecedented scales, and trade that carried species and pathogens across continents. Seen from the vantage of deep time, Homo sapiens' recent conquest of planetary influence reads as an exponential curve superposed on a very long, flat baseline. For billions of years, biogeochemical cycles oscillated within relatively slow bands. Then, in the sliver of recent prehistory, where humans become numerous and technologically potent, rates of carbon extraction and dispersion, species translocation, and landscape modification climbed dramatically. The Anthropocene, whether formally declared or not, is the geological name for this step change, a time when a single species begins to drive measurable shifts in atmospheric composition, sedimentation patterns, and biodiversity. Emotion enters this account not as melodrama, but as an ethical and existential contour. The collective psyche of humans across millennia appears marked by contradictions. Extraordinary empathy within groups and frequent violence between them, a capacity for imagination and tenderness, and, in other contexts, for extraction and domination. The same mental tools that enabled shared myths and collaborative projects also made possible technologies that can destabilize planetary systems. This moral ambivalence complicates any simple narrative of progress. Where earlier species dominated through sheer biomass or long-term chemical alteration, humans dominate through cognition. Symbolic thought applied at scale, and the moral weight of that capacity is inescapable. Finally, the material traces of Homo sapiens present a double lesson. On the one hand, recent technological outputs, plastics, concrete, fly ash, novel isotopic signatures, nuclear fallout, are geologically stubborn. They will leave recognizable markers in the sedimentary record. On the other hand, much of the quotidian culture text on perishable media, wooden dwellings, ephemeral rituals remains fragile against the patient erasure of erosion, subduction, and time. The irony is that the very species that learned to externalize memory so richly in art and writing is also subject to the same geological amnesia that erased much of the planet's deeper past. To close the scene is to hold a paradox in both hands. Homo sapiens is at once astonishingly new and profoundly consequential. In 300,000 years, a lineage that once eked out existence on marginal savannas learned to carve tools, to shape fire, to speak symbols into being, to build dense societies, and finally to alter the chemistry of the planet. That ascent carries wonder and warning. Wonder at the species' capacity to imagine and to create. Warning because the accumulated effects of those creations now pose questions about resilience, ethics, and the kinds of futures that will be legible in the strata. The chapter about human emergence ends not with a tidy moral, but with an open question. How will a species that learned to read the deep past choose to write its own pages into Earth's record? What does a civilization look like when held against the ruler of rocks and the calendar of continents? It is easy to imagine cities as lasting things, stone that resists rain, texts that survive, monuments that anchor memory. But geology tells a different story. 5,000 years of recorded human civilization is a single, fragile flash in an archive that spans billions of years. The contrast is not merely numerical. It is a difference in tempo, in material persistence, and in the kinds of memory each system keeps. This is a meditation on how social contracts and collective intelligence, those invisible architectures of cooperation and meaning, become, for an instant, a force that can register in the planet's deep memory. Civilization, in the narrow sense, is young, if one counts the earliest written records, the first cities, and the consolidation of institutions that manage surplus and dispute. 5 millennia is the scale. Agriculture and sedentary settlement reach back beyond that in places and periods, but complex states, literate bureaucracies, and market networks that span regions are recent inventions. Industry, fossil fuel-driven, mechanized production has been with the species for barely 2 centuries. Those 2 centuries have multiplied the reach and intensity of human action by orders of magnitude. Energy per capita, the mass of materials moved, and the speed at which information flows have accelerated so rapidly that the geological baseline reads the modern era as an unusual spike. It is tempting and comforting to equate this sudden acceleration with permanence. The very technologies that enable long-distance travel and instantaneous communication, steel, concrete, fiber optics, satellites, project an illusion of durability. They feel like infrastructure of the eternal. Yet durability is context-specific. Stone endures against wind and water for centuries, but stone can be buried under volcanic ash or subducted into the mantle. Paper archives can survive in dry caves. Digital archives can persist on redundant servers. Both can be erased by fire, flood, corruption, or simply the deterioration of a medium. Collective memory is as much a function of distribution and maintenance as of the intrinsic toughness of materials. At the heart of civilization lies a social contract, a set of tacit and explicit agreements that enable strangers to cooperate at scales far beyond kin groups. Those agreements are not written purely in ink. They are encoded in laws and contracts, in ritual and habit, in currency and promises, and in institutions that enforce, remember, and transmit. Writing, record-keeping, and ritual formalize obligation. Markets convert trust into exchange. Bureaucracies convert behavior into legible data. These social technologies are the scaffolding on which large-scale cooperation rests. Without them, the web of interdependence that powers cities and economies would collapse into small, local reciprocity. Collective intelligence is the living product of those scaffolds. It is not simply the sum of individual minds, but an emergent property of networks, artisans sharing techniques across generations, scholars building upon predecessors' insights, traders and mariners refining routes through accumulated practice. Libraries, guilds, and, more recently, research institutions act as memory repositories, allowing knowledge to be transmitted across time. Each active inscription on clay, papyrus, parchment, or silicon is a way for a community to externalize cognition, to create a public brain that outlives the individual. The emergence of writing was a pivotal moment in this story. Before writing, knowledge circulated through embodied practice and oral performance, powerful in its own right, but necessarily local in its fidelity. Script allowed an economy of remembrance that could support complex administration. Land records, tax registers, contracts binding distant strangers. The externalization of memory changed the social contract. It made promises enforceable beyond immediate reputation. It allowed systems of law and governance to scale. With writing also came the possibility of institutional continuity archives that could be consulted centuries later, and traditions that could be rationalized and transmitted. Cumulative culture amplified human capacity further. Tools were improved across generations, not just by trial and error, but by the conscious transmission of designs. Elaborate division of labor specialists in metallurgy, ceramics, mathematics, navigation arose because social institutions could support them. Specialized knowledge, when pooled, creates emergent capabilities, canals that distribute water across landscapes, maritime routes that knit continents together, markets that allocate resources with staggering efficiency. Those capabilities, in turn, create new environments. irrigated plains, terraced hillsides, urban agglomerations. So that culture becomes a form of niche construction, the deliberate shaping of environments to meet human ends. Yet the most striking feature of modern collective intelligence is its speed. Science, as an institutionalized method of inquiry, creates an unusual kind of cumulative knowledge, probabilistic, replicable, and self-correcting. Scientific networks are webs that process data, cultivate doubt, and refactor understanding. When coupled with industrial power, the output of these networks becomes material. Discoveries in chemistry and physics quickly translate into technologies that reshape landscapes and atmospheres. The social contract with science is peculiar. It trades local certainty for distributed, peer-reviewed confidence. The result is a global acceleration, the Great Acceleration, that, in fewer than 2 centuries, has altered atmospheric chemistry, shifted biogeographic patterns, and rewritten sediment budgets. What, then, are the material traces? If civilization is brief in geological terms, can its fingerprints survive? The answer is both bleak and startling. Some traces are ephemeral and will vanish almost without a trace. Organic textiles, wood-framed buildings, ephemeral digital formats, they rot, burn, or degrade. Yet other traces are stubborn, chemically and physically. Layers of concrete and asphalt lithify into a lens of unnatural rock, plastics fragment and become ubiquitous microplastics. Embedded in marine and terrestrial sediments, heavy metals and rare isotopes concentrate in sediments near industrial centers. Radionuclides from nuclear testing leave a time-stamped global marker. Where humanity has altered the ratios of carbon and nitrogen in soils and oceans, those anomalies will be recorded in isotopic excursions. Large-scale mines and tailings create lithological anomalies, an unnatural stratigraphy of scarred Earth. These materials constitute a stratigraphic signal that future geologists could, in principle, read. The mid-20th century acceleration of nuclear fallout produced a near-synchronous global layer of isotopes, an unambiguous dated marker. Plastics, ubiquitous and chemically novel, pervade sediments in ways without obvious natural analogues. Concrete accumulations may form a dense, chemically distinct stratum. Yet the differences between a legible marker and a readable narrative are important. A future analyst might detect anomalies, ratios of elements out of balance, sudden increases in sedimentation rates tied to mining, spikes in black carbon, and infer a global perturbation. Whether that analyst could reconstruct the cultural meanings, the institutional subtleties of law and ritual, or the narratives encoded in texts, is another matter entirely. The fragility of cultural memory is not only about materials. Social systems themselves can collapse. Centralized institutions, while efficient, create single points of failure. Complex supply chains, reliant on fossil energy and just-in-time logistics, are vulnerable to disruption. When administrative capacity decays through war, ecological crisis, or institutional breakdown, writing and records become brittle. Libraries burn, archives delaminate, and the rituals that bind large groups fray. Civilizations have risen and fallen in cycles that archaeology shows again and again. The energetic intensity that enables complexity also creates dependencies that can unravel. Those collapses are not merely socio-economic. They translate directly into the likelihood that particular artifacts or records will persist into deep time. There is a philosophical tension here. Humans build institutions to coordinate action at scale precisely because the raw biological capacities of individuals' strength, memory, lifespan are limited. Institutions extend those capacities. Education, law, markets, religious systems, and bureaucracies become the distributed hardware of collective intelligence. They allow planning across generations, the accumulation of technology, and the management of ecological systems. But institutions must be maintained. They demand energy, fidelity, and recruitment of belief. When belief erodes or energy flows stall, institutional memory decays. Thus, the very thing that makes civilization possible, the social contract, remains contingent upon the long-term maintenance of practices and material networks. Collective intelligence also carries unusual resilience. Distributed knowledge systems, cultural redundancy, and durable symbols can persist in pockets even after central collapse. Oral traditions, ritualized practices, and resilient small-scale technologies, terracing, seed storage, pottery, can survive in marginal settings and later seed recovery. In other words, the erasure of grand monuments need not mean the erasure of all human ingenuity. Much of it persists in the workaday competence of groups that never made it into the historical spotlight. The ethical implication of this duality is not abstract. If human actions can leave a measurable geochemical signature, then civilization becomes an act of planetary engineering, whether intentionally framed as such or not. Building, burning, cultivating, emitting. These are modes by which social contracts externalize their collective will into the environment. With the cognitive capacities that enable reflection also comes the capacity for stewardship. The same collective intelligence that can fragment into destructive feedbacks can be marshaled to design institutions that modulate impact, to choose materials with an eye toward longevity or recyclability, to manage carbon flows, to preserve distributed archives, and to design redundancy into critical systems. Yet stewardship is political and cultural work. It requires trust across scales, from local communities stewarding watersheds to international bodies negotiating atmospheric commons. The architecture of cooperation must widen. Legal frameworks, cultural norms, and economic incentives must align to support long-term choices. This is the social contract writ into planetary stewardship, a collective agreeing across time and space to constrain short-term advantage for the preservation of future options. It is a fragile bargain. History is full of bargains broken under pressure. Still, the existence of such a possibility reframes the human blink not as an inevitability, but as a choice with moral weight. Speculative questions sharpen this reflection. If a far future geologist or alien scientist were to sift through strata which aspects of human civilization would be legible, they would likely find a layered signal, an abrupt rise in carbon flux and greenhouse gases, isotopic anomalies in nitrogen and sulfur tied to industrial fertilizers and combustion, concentrated anthropogenic sediment in deltas and coastal basins, technofossils, plastics, alloys, concrete embedded in a thin but globally distributed horizon. They might find mined landscapes, canals, and buried urban lithologies. They would recognize a global perturbation. What they would not easily read are the finer grain of human meaning, the laws, the rituals, the languages, the decisions, and the social contracts that shape behaviors. Those require social minds to interpret. That epistemic gap is both sobering and energizing. It suggests humility. Most of the things that matter deeply to humans, the poems, the moral arguments, the tender acts of care, are ephemeral against deep time. It also offers an ethical urgency. If the artifacts of civilization that are most likely to persist are the ones associated with extraction and waste, then those are the aspects of culture most likely to be judged by the planet. Choosing different materialities and trajectories is a way to influence what the stratigraphic book will later whisper about us. Ultimately, the image of human civilization as a geological blink should not be only a humbling datum. It can be a prompt to reconfigure social contracts and collective intelligence toward longevity, writing institutions that can outlast immediate crises. Distributed, redundant, repairable becomes a cultural technique. Designing economies that internalize long-term ecological costs is another. Cultivating forms of memory that do not depend on single sites or fragile media, diversified seed banks, decentralized data protocols, community-held knowledge are ways in which the social contract can expand to encompass geological time. The paradox remains gripping. In a temporal sense, humanity has, in a few thousand years, contrived systems that rival the slow work of microbes in their capacity to alter chemistry and redistribute mass. In a material sense, much of that work is fragile, liable to be erased by the slow actions of plate tectonics and diagenesis. Socially, humans are capable of binding strangers into enormous cooperative projects, but those bindings depend on fragile institutions and energy flows. To stand at this hinge is to hold two truths: that human civilization is brief and vulnerable, and that it has produced an unusual kind of agency, the ability to consciously reflect on and alter its own trajectory. If geology is patient enough, the question narrows into a ledger: what will remain of human intent? The planet would preserve certain anomalies, chemical, lithological, and morphological, that testify to a species with extraordinary agency. It will not, however, easily preserve the meanings behind those anomalies. That lack of semantic continuity is the challenge for collective intelligence, to craft durable legacies that carry not only materials but legible values. To do that requires a social contract that takes the horizon of centuries and millennia seriously, one that binds generations through institutions and practices calibrated to deep time. The final image is a simple one: a thin, bright layer in a sedimentary column stamped with strange materials, odd isotopic ratios, and the mineral ghosts of cities. It is a mark! A human exclamation in a book of slow sentences. If that mark is all that remains, then the planet will record that a species once learned to cooperate across vast scales and to bend energy and matter at will. Whether the coda after that mark reads as a warning, a triumph, or an unremarkable perturbation depends on choices made now, on the social contracts that govern the distribution of costs and responsibilities, and on the forms of collective intelligence humanity cultivates in the decades to come. What does it mean, in a language of epochs, to become not merely a species on a planet, but an actor that rewrites the planet's grammar? That question opens this chapter. It asks how a species whose history spans a geological heartbeat has come to unfasten the geochemical anchors that kept Earth's systems within certain bounds for millions of years. The image to hold is not a single city or a single industry, but a diffuse choreography of clearing, burning, digging, and dumping that, over a few centuries, nudges climate, soils, and seas beyond their accustomed rhythms. The first and most intimate of these interventions is deforestation. Trees are slow agencies of chemistry and hydraulics. They lift water from the soil and return it to the atmosphere. Their roots bind the earth and their leaves modulate sunlight and microclimates. When intact, forests are sediment managers. They trap carbon above ground in trunks and leaves and below ground in soil organic matter. To remove them is to cut an organism out of the planetary metabolism. The act of deforestation can be described in 1,000 quiet scenes: an expanse of cedar trunks scored by metal, the dull hum of chainsaws, fields of stumps left like teeth broken out of a jaw, the thin gray of smoke rising from slash burning. But these domestic images accumulate into a planetary process, where wide tracts of forest vanish, rainfall patterns change, evapotranspiration declines, local cooling fades, clouds condense less readily, and landscapes that once recycled water begin to run drier. Soil, exposed to sun and rain, oxidizes and erodes. Carbon, once sequestered in living tissue and peat, is released as carbon dioxide. What is local becomes global. 100,000 clearings here and an agricultural conversion there aggregate into measurable increases in atmospheric CO2 and altered regional hydrology. In geological terms, deforestation writes a steady anthropogenic abrasion across the stratigraphy charcoal layers. Unusual charcoal-coal ratios, sudden shifts in pollen types, and isotopic signatures that betray a moved balance between woody and herbaceous biomass. Closely bound to clearing is the transformation of land for agriculture. It is a story of domestication and dependence, of selective breeding and sediment flows. The plow, the irrigation channel, the terraced slope, all are technologies of niche construction. They are ways in which a species reconfigures a landscape's carrying capacity to feed more mouths. Early terraces spoke of careful engineering, of soils kept in place and water conserved. Later, the industrialization of agriculture turned that care into extraction at scale. Fertilizers flooded fields, nitrogen fixed from the atmosphere by industrial chemistry changed nutrient cycles. The result has been a global acceleration of nutrient fluxes. Rivers now carry unprecedented loads of nitrogen and phosphorus into seas, igniting blooms of algae that, when decomposed, consume oxygen and create dead zones. Those dead zones are not metaphor. They are chemical scars that will fossilize as black, organic rich layers in future sediments, the signatures of a new mode of planetary metabolism driven by synthetic compounds. If forests and farms alter the surface and soils, extraction reaches down. Mining and quarrying are direct acts of geological rearrangement. They remove crustal volumes, concentrate metals, and discard residues in heaps and tailings that leach novel chemistries into waterways. Open pit mines scar landscapes at scales that rival natural erosion, and the waste they produce carries heavy metal signatures and acid drainage that propagate to watersheds. The global appetite for energy has carved similar marks. Coal seams are plumbed and burned. Oil is pumped from ancient decomposed biota and combusted into the atmosphere. These processes free ancient carbon that had lain sequestered for millions of years and release it rapidly into the air in forms that alter the radiative balance of the planet. The climate response to these releases is an accent of speed rather than novelty. Earth has warmed and cooled many times, but the present rate of atmospheric change is abrupt on geological scales. The Paleocene, Eocene, thermal maximum, PETM, an event roughly 56 million years ago, provides a distant analog, a rapid injection of carbon into the atmosphere, a spike in global temperatures, and profound biotic turnover, particularly in the oceans. Difference now is the compressed time scale, where the PETM unfolded over tens of thousands of years, fossil fuel combustion has delivered a comparable mass of carbon in mere centuries. The importance is not only the degree of warming, but the velocity. Many ecological and geochemical processes are already sensitive. Soils, forests, coral reefs, and ice sheets respond differently when stress arrives slowly versus when it arrives as a shock. Rapid warming stresses systems' adaptive capacities, pushing biomes toward tipping points. Permafrost thaws and releases methane. Ice sheets destabilize and contribute to sea level rise. Ocean circulation patterns shift, and species face migration barriers that cannot cross fast enough. Mass extinction is, in part, a function of these broken rhythms. The fossil record shows that tipping points cascade. Ocean acidification, deoxygenation, warming, and habitat loss can act in concert to remove ecosystems. Coral reefs, stations of biodiversity analogous to rainforests on land, are particularly sensitive to temperature and acidity. When reefs bleach and die, they do not simply vanish quietly. The structural complexity they provide collapses, with ripple effects across food webs. Fisheries collapse, coastal protection erodes, and carbonate sediment budgets shift. The modern indicators are not hypothetical. Oxygen minimum zones are expanding, plankton communities are reorganizing, and species are moving poleward or to deeper waters. Pollution expands the catalog of forcings beyond carbon. Plastics, an emblem of modernity, fragment into microplastics that pervade soils, rivers, and oceans, entering food chains and seeding sediments with synthetic polymers that have no natural analog. Persistent organic pollutants, PCBs, dioxins, flame retardants, bioaccumulate and biomagnify. Heavy metals such as lead and mercury appear in ecosystems at concentrations that were unknown in pre-industrial times. New isotopic markers from nuclear testing led to synchronous spike in radionuclides across global strata in the mid-20th century, a kind of inadvertent global timestamp. These substances are geochemical annotations. They tell a future reader that something novel and artificial was dispersed widely and rapidly. Urbanization and the mechanization of transport layer, another set of imprints. Road networks reroute waters, fragment habitats, and concentrate runoff. Cities concentrate heat, altering local microclimates and island-like patterns and their material base concrete, asphalt. Steel accumulates as lithified, anthropogenic rock. Sewage and industrial effluents change river chemistry. Dams interrupt sediment flow. Starving deltas of the silt that once built land at the interface of river and sea. Coasts, where much of human infrastructure clusters, feel the compound effects. Subsidence from groundwater extraction plus rising seas equals accelerated inundation. The geological result is a rewarped coastline, smothered estuaries, and trapped pollutants that will leave recognizable layers in future sediment cores. The velocity of change is crucial because biological systems often require time to adapt. Evolution operates as a slow, patient tailoring. Populations can shift their traits given generational time. But when environmental parameters move faster than generations can turn, adaptation lags and extinctions gather. The current Anthropocene surge is not merely additive, it is multiplicative. Multiple stressors act simultaneously in ways that past biospheres seldom experienced together. Climate change, habitat loss, invasive species, overexploitation, and pollution converge, creating novel selective landscapes. Where once mass extinctions were usually triggered by singular global forcings, volcanic supereruptions, bolide impacts, now a mosaic of smaller human-driven pressures, can have equally devastating cumulative effects. There is an effective register to this recognition. Humanity, at once inventive and small, evokes a conflicted sentiment in the geological story. Pride for the cognitive capacities that made metal and theory possible, and a quieter, more complicated sorrow for the fragility those same capacities have revealed. In the collective mind, there is often a tension between immediacy and foresight. Short-term incentives concentrate attention on productivity and growth, but geoscales demand an ethic of patience. The mismatch between political cycles, market quarters, and the slow crocks of ice and soil can explain much of the inertia that greases the engine of planetary change. Cognitive biases, discounting the future, privileging present gains, wanting certainty where only probabilistic forecasts exist, are not moral failings so much as evolutionary legacies ill-suited to stewardship across centuries. Yet the geological record also offers a pragmatic lesson. Interventions leave detectable signatures. If one imagines a future researcher parsing sediment columns, several anthropogenic fingerprints will be clear. The mid-20th century radionuclide peak is an almost unambiguous horizon. Elevated concentrations of nitrogen and phosphorus in coastal sediments correspond to modern agricultural runoff. Microplastic shards appear throughout recent deposits. Rapid increases in black carbon and polar snow indicate industrial soot transported globally. And perhaps most consequentially, a persistent global rise in carbon dioxide and the associated carbon isotopic excursion will be recorded. A chemical exclamation in the Book of Sediment. That ledger reframed responsibility as not merely moral but forensic. The Anthropocene can be read as an experiment with planetary systems, and experiments have consequences. To alter the rate of greenhouse gas emissions, to protect remaining old-growth forests, to redesign agricultural systems, to remediate polluted waters. These are not merely ethical choices, they are the techniques by which a species can modulate its signature on Earth. The practicalities are complex. Technological options exist for carbon capture and storage, for alternative energy, for circular materials, economies that reduce the flow of novel compounds into the biosphere. Political and social systems must be configured to incentivize long-term thinking, to internalize environmental externalities, and to redistribute the burdens of transition fairly. There is a quieter, almost elegiac observation in all of this. For most of its tenure on Earth, life altered environments slowly enough that feedbacks and adaptations had time to knit themselves together. Microbial mats rewrote chemistry over millennia, forests sequestered carbon across long times, reef communities constructed habitats over generations. Humans have compressed many of these processes, converting slow accretion into abrupt incision. The consequence is not solely loss. The capacity to deliberate collectively, institutionally, scientifically affords the possibility of repair. Unlike the eruptions of flood basalts or the strike of an extraterrestrial bolide, human-driven changes are reversible in principle, if not always easy in practice. Emissions can be reduced, forests can be regrown, pollution can be remediated. Such acts require coordination across scales and generations, the very kinds of social contracts that have enabled civilization's brief flourish. The final image in this part resists melodrama. It is a pair of comparative scenes folded into one frame. On one side, a sedimentary column, red like a ledger, will contain a thin yet globally distributed horizon, plastics, altered isotopes, heavy metals, radionuclides, and a sharp excursion of carbon dioxide. On the other side, a patchwork of landscapes, managed forests, terraced fields, engineered coasts, is shaped by practices, laws, markets, myths, and the accumulated knowledge of communities. Which of these scenes will be dominant in the deep future is not predetermined. The geologic record will preserve the fact of alteration. Whether the narrative reads as catastrophic collapse or as a pivot toward sustainable stewardship depends on choices enacted now, policies, innovations, cultural commitments, and the willingness of a species to view its temporal reach as morally significant. Thus, humanity stands in geological terms at a choice point. To become a durable agent in Earth's history is to learn how to inhabit the apparatus of planetary engineering responsibly, to modulate rates, to avoid tipping cascades, to design with the long horizon in mind. The fact that an entire planet's systems can be altered by tools and institutions of human making is both a profound responsibility and a rare opportunity, not merely to leave a slower, gentler stratigraphic mark, but to craft a story in which the capacity to change the world is matched by the wisdom to preserve it. What if absence could be read like a text? What would the planet say many pages from now? If humankind simply stopped turning the page? That question, quiet, unnerving, and oddly precise, frames an experiment of imagination and geology. It asks not whether the Earth would notice the departure of its most noisy occupants, but how it would answer that absence, by erasing, by repairing, by inventing new rhythms that never once resembled human schedules. The first answers are startlingly immediate. The electrical hum that defines modern nights would die in hours. Within a day, the lights across continents would stop their synchronized flicker, transportation systems would halt. Trains trapped between stations, planes parked and slowly drained of fuel until spilled kerosene ignited or evaporated. Pumping stations would fail in sequence. Sewers and water treatment plants, machines designed to keep human waste apart from living waters, would clog, overflow, and then stagnate. In cities where heating relied on centralized gas or electricity, pipes would freeze in winter. In temperate zones, heat would empty from offices and hospitals, museums, leaving fragile objects to the slow creep of humidity. Those first weeks and months would be an ecology of breakdown. Fires started from overturned appliances or from unattended industrial processes could flare until they starved for fuel. Smoke would condense on buildings and in valleys where temperature inversions trapped it. With maintenance absent, containment systems at hazardous sites would leak. Nuclear facilities, designed with automated fail-safes and redundant cooling, may scavenge their own reserves for a while, but over years the risk of localized meltdowns and contamination increases where active human control lapses. Yet these events would be pulses, unlucky, dramatic, noisy against a broader process that is slower and greener. Vegetation advances with an almost theatrical impatience. The first colonists are the pioneers familiar to every ruined lot and abandoned road, lichens and mosses on stone, grasses in the cracks of asphalt, annual weeds that make a year's lifetime between an empty parking lot and a collapsed storefront. These organisms are biogeographical locksmiths. They pocket fragments of dust, hold moisture, and make a thin living soil out of what was once sterile rubble. In the first seasons, seeds carried by wind and birds find new niches, the raised beds of median strips, the filigree of gutter sediments, the shallow blankets of soil and planters. Roots find the mortar beds between bricks, pry them apart incrementally. Fungi colonize drywall and damp wood, secreting enzymes that dissolve what humans treated as durable. Within a decade, saplings, birch, willow, poplar push up through collapsed asphalt and into the interiors of once sealed buildings. Where urban design had been geometry and control, nature returns to stochastic processes, opportunistic growth, succession, and the patient matrix of symbiosis. Concrete, so emblematic of permanence in human imagination, is vulnerable in time frames that surprise non-geologists. Concrete is a composite that resists weather for centuries in favorable climates, but it is not immune. Freeze-thaw cycles wedge water into pores, roots and fungal hyphae seek out minute weaknesses, chemical processes such as carbonation and alkali-silica reactions alter the cement matrix. Steel reinforcement bars, rebar corrode once the protective alkaline environment around them is compromised, expanding and cracking the surrounding concrete. Over decades and centuries, facades spall, roofs sag, and skeletons of buildings become open frames. Glass, brittle but chemically inert, shatters and is scattered. Panes may survive in sheltered piles, but the orderly geometry of skyscrapers becomes a tangle of rusted beams and forest. The canopy grows where hands no longer prune. Within a human lifetime span, suburbs turn to thickets. Within a few centuries, former agricultural valleys can revert to forest. The species mix, however, is not the same as before humans. Edge species, those that thrive in disturbed land, tend to dominate early regrowth. Oaks and pines will reoccupy terraces, invasive plants that once spread with the accoutrements of trade grasses, vines, mines. Shrubs become foundational. Animals follow. Synanthropic species, rats, pigeons, feral dogs, house sparrows initially capitalize on abandoned food caches and structures. But as the landscape shifts toward woody succession, new opportunities open for deer, boar, foxes, and birds of prey. In places where agriculture once constrained megafauna, those niches may be reoccupied or reshaped by descendants of domesticated species that went feral cattle, goats, sheep, undergoing selection in truly novel contexts. What the casual eye calls recovery is, in ecological terms, succession and transformation. The planet does not aim to reconstruct a pre-human Eden. It builds new assemblages shaped by legacy effects. Soil altered by centuries of tilling has different horizons and compaction. Seed banks reflect a century of crops and weeds. Rivers churn sediment differently because of dams and deforestation, at least until those structures fail and are reworked by floods. Nutrient flows, particularly nitrogen and phosphorus loaded into rivers by agriculture, leave their trace in eutrophic blooms that may persist for decades or centuries, forming black, organic, rich layers in coastal sediments. Microbial communities in soils and oceans already shifted by prolonged human activity will continue to respond to changing chemistry, forging pathways that diverge from pre-anthropogenic conditions. The archaeological imagination loves to ask what will remain recognizable. The blunt answer is remarkably little of the cultural meaning, much of the chemical signature. Stone foundations may survive for millennia in arid climates. Ceramics and certain glass artifacts are resilient. Bronze and certain metals can persist as verdigris, patinated objects. But the bulk of the human technosphere, wooden houses, textiles, paper, the vast archives kept in servers reliant on electrical infrastructure are ephemeral. Plastics complicate the calculus. Some polymers resist biodegradation, fragmenting into microplastics that become omnipresent in sediments, soils, and organisms. These fragments will be part of a stratigraphic horizon, a novel chemical fingerprint, a thin but globally distributed layer that indicates something artificial and sudden. Metallic alloys will corrode, aluminum may oxidize and disperse, titanium and certain ceramics might persist longer. Nuclear fallout leaves isotopic markers, spikes of plutonium and other radionuclides that serve as an almost unambiguous, synchronized timestamp across the globe. In the long ledger of sediments, therefore, one finds not monuments, but anomalies, a pulse of odd elements. Isotopic ratios shifted by fossil fuel combustion, concentrations of plastics, and a thin horizon of technogenic debris. Timescales matter when the narrative moves beyond immediate reclamation to deep recovery. Within centuries, much of the recognizable architecture will be obscure mounds and fieldstones. Within a millennium, floodplains and river deltas will have buried many low-lying ruins under fresh sediment and alluvial reworking. Coasts, dynamic already, will claim or conceal cities depending on sea level changes and sediment supply altered by dam failures and erosion. Over tens of thousands of years, much more is possible. Species radiations, the emergence of new ecologies built on the niches created by human artifacts. Inverted landscapes, subways turn aquifers, reservoirs silted over into wetlands become unique habitats. Evolution is patient, but not indifferent. Given enough time, isolated populations derived from commensal species could diverge into new taxa adapted to the novel. Environments of ruins, cave networks, and subway tunnels could foster troublophilic organisms. Seed-eating rodents might evolve skull shapes adapted to plastic-based diets. Microbes, those ancient, persistent engineers, are likely to be the most inventive readers of human chemistry. Bacteria and fungi that metabolize hydrocarbons, plastics, and synthetic compounds are already proliferating in a world without consistent human interference. Such lineages could diversify enormously, rewriting food webs on scales chemistry alone can judge. Yet there are limits to recovery and to the idea of a pristine rebound. Certain effects of human activity persist on timescales that are geologically significant. Elevated atmospheric CO2 remains in the system long enough to alter climates for centuries to millennia. Ocean acidification, which dissolves carbonate shells and impacts calcifying organisms, operates on timeframes that slow the reconstitution of reefs and carbonate platforms. The silicate weathering feedback by which rocks draw down carbon dioxide acts over hundreds of thousands of years. Thus, the planet's climate may not return to pre-industrial levels for many millennia without active removal of anthropogenic carbon. Some biotic losses, extinctions among large-bodied animals. Certain island endemics are effectively permanent. The genetic lineages are gone, and their ecological functions may be replaced by different combinations of organisms, but the specific forms are lost. Geology keeps a parsimonious record. Over a few million years, tectonics and erosion will recycle shallow crustal volumes. Sediments lithify, are uplifted, eroded, and, in time, can be subducted into the mantle. The physical monuments of a global civilization, roads, cities, monuments mostly occupy the thin veneer of continental crust that is most fragile to the planet's recycling machinery. Thus, in the very deep future, tens of millions of years, the odds that a visitor could identify a city as such based solely on physical remnants are slim. What persists will be intangibly chemical. Isotopic shifts in carbon and nitrogen in sedimentary organic matter, anomalous metal concentrations, and the global layer of techno-fossil fragments embedded within stratigraphy. These are the palimpsests that future geologists might use to mark an Anthropocene horizon. There is a tenderness to the idea of Earth's recovery, mingled with a note of melancholy. Recovery is not restoration to a previously known state. It is the planet reorganizing itself according to new initial conditions. The plant communities that return may be different in composition, the animal assemblages unfamiliar, and the soils recalibrated by a legacy of agriculture and pollution. Yet the resilient processes, succession, mutation, dispersal, symbiosis, are robust. Life has a long record of filling new niches after catastrophic resets. The empty cityscapes would become laboratories of evolutionary experimentation. New combinations of species adapt to the microclimates of ruins, to the chemically altered soils, to plastic-rich detritus, and to hydrologies rerouted by failed engineering. There is also, in the imagining, an ethical echo. To think of a world without humans allows both sorrow and relief to enter the same thought. Relief, because the planet's fundamental biogeochemical systems are likely to stabilize over the long run, and many ecosystems will regrow their structural complexity. Sorrow, because human cultures, the intangible architectures of meaning, art, jurisprudence, and love are unlikely to be legible to geological readers. The books, the songs, the moral projects, the weight of what humans valued are fragile, embedded in media and practices that require continuous maintenance and social transmission. Their disappearance is not merely an ecological footnote, it is the erasure of modes of consciousness. Still, the planet's narrative is not merely about loss. It is also a long lesson in the durability of small things. Microbial mats, the resilient bones of stromatolites, the persistent chemical signatures of metabolic activity, these are the real continuity of the biosphere. The human chapter, if removed in bodies, will persist in chemistry. Isotopic anomalies, technofossils, and stratigraphic horizons will testify that for a brief geological instant, a species learned to alter its planet in novel ways. That testimony is both a stain and an archive, evidence of agency writ into the crust. In the speculative silence that follows such imagining, a final, sober idea asserts itself. Absence is not the undoing of responsibility. If it is imaginable that Earth can heal, and that much will be erased, it is equally true that the chemical and ecological sentences written by humans will be read by future beings, geologists, descendants of surviving lineages, or even other sentient species, if those readers have the skill to decode isotopes and layers. The mark left by a species is therefore not merely a forensic curiosity, it is an ethical ledger. To shape what remains, to decide whether the Anthropocene horizon will be a thin scandal or a curated archive of learning, is to accept a form of stewardship that lasts longer than a political term or an economic cycle. So the closing image is twofold: a city, silent and green, its streets braided with roots and its towers softened into cliffs of vegetation, and, beneath that, a cross-section of sediment, a thin, bright stripe of unusual chemistry and foreign compounds, plastics, radionuclides, altered carbon ratios, the geological whisper that says, in no ambiguous terms, that a species once tried to manage a planet and left a footprint. The Earth will remember. It will also move on. The question for any species that can ask it is what kind of memory it chooses to inscribe. What if humanity is not an apex but an episode, an intense, articulate footnote in a book that has turned many hands before and will be read by many hands after? The comparison is not merely rhetorical. Dinosaurs, once the dominant engineers of ecosystems for more than 100 million years, are now a fossil chorus. Bones, footprints, faint chemical traces. Their reign reads as a long paragraph, then a line break, and then new prose begins. The question at hand is a simple, disquieting rearrangement of perspective. Could Homo sapiens occupy the same kind of paragraph, striking, meaningful, but ultimately bounded? And, when that paragraph ends, will something else rise to tell a different story? The idea stretches the mind along two axes, time and contingency. Temporally, human civilization is geologically brief. The chronology sketched earlier is unforgiving. A few millennia of cities and industry are pinpoint against the slow sweep of the planet. Contingently, Earth's history shows that dominance is rarely permanent. Empires of organisms, microbial, plant, reptilian, mammalian, have risen, altered chemistry and geography, and then given way to new regimes after crises or slow rebalancing. Against those patterns, the possibility of a successor is not fantastical. It is an intelligible inference. Ecosystems reconfigure, selection continues, and novel niches unfold where predecessors have left vacancies. But imagining successors requires careful anatomy of possibility. It is not a theatrical prophecy of inevitable replacement, so much as a set of constrained scenarios, each weighted by physical principles, evolutionary logic, and the messy history of chance. One evident path is the microbial. Microbes have been Earth's most durable engineers for billions of years. They can exploit almost any energy gradient, remodel chemical cycles, and capitalize on environments that larger life cannot endure. If humans vanished, microbes would be the first responders and, in many senses, the long-term victors. They would metabolize wastes, colonize petrochemical residues, and evolve to digest synthetic compounds that currently bewilder natural enzymes. Already, certain bacteria and fungi that metabolize hydrocarbons, plastics, and complex xenobiotics exist. Given time and selection pressure, the descendants could radiate into lineages that dominate altered biogeochemical regimes. The successor in this frame is not a single charismatic organism, but a distributed, invisible empire. Mats and tidal flats that bind novel sediments, chemosynthetic communities in polluted sediments processing new energy flows, and microbial consortia that fix and recycle elements in ways that leave distinct isotopic footprints. In the geological record, such a transition might look less like a change in form and more like a rearrangement of chemical ratios. Carbon, nitrogen, sulfur isotopes shifted in unusual ways, organic rich layers laced with synthetic residues. Another plausible trajectory follows from the niches humans have themselves created, synanthropic landscapes unnaturally favorable to certain species. Rats, pigeons, feral dogs, mice, and certain weedy plants thrive in human-dominated environments. When cities fall silent, these organisms either collapse with their resource bases or, more likely, diversify in place. Over long timescales, isolated pockets of commensal species, populations fragmented by geography but exposed to novel selection. Pressures could undergo speciation and morphological change. Ecologists point to island radiations and post-catastrophe adaptive radiations as analogues. Small founder populations, strong selective filters, and abundant empty niches can produce rapid evolutionary turnovers. A future fauna that occupies old urban canyons and reclaimed farmlands might bear the genetic ghosts of domestication. Changed dentition in rodents eating novel food types, altered life histories in birds that no longer depend on human refuse, physiological shifts in animals exposed to persistent pollutants. These successors would not be post-humans in any cultural sense. They would be organisms sculpted by the legacy of human presence. A third possibility grows from the handprint of human technology itself. Humans have not only reshaped landscapes and chemistry, they have designed life in laboratories and assembled computational networks that behave in ways biological evolution never anticipated. Synthetic organisms, engineered microbes, gene drives, and cultivated symbionts are nascent actors whose long-term evolutionary trajectories are uncertain. If synthetic life forms escape containment and persist, they may blend evolutionary and technological logics. Engineered microbes that metabolize plastics or heavy metals, for instance, could become part of new microbial consortia, embedding human design principles into ecological function. Gene-edited organisms released intentionally or accidentally could rewire food webs. These engineered lineages could leave particularly legible chemical or genomic signatures, entirely novel metabolic pathways, chimeric genetic sequences with recognizable engineered motifs, and global changes in degradation pathways that alter how organic material preserves in sediments. In time, an observer curious about the past might find genetic oddities in ancient DNA sequences, unnatural motifs that betray design rather than slow, undirected mutation. Alongside biology, there is the quiet but consequential possibility of non-biological successors. Machines, networks, and artifacts are not alive by standard biological definitions, yet they persist, replicate in limited fashion, and exert systemic effects. If technological systems gained forms of self-maintenance and autonomy prior to a human, exit distributed energy harvesting networks, self-repairing infrastructure, or machine learning systems embedded in industrial processes, there would be an imperfect continuity between the biosphere and a technosphere. The plausibility of machines long outlasting their creators depends heavily on material constraints, energy inputs, resource access, and the vulnerability of physical substrates to corrosion and decay. In most scenarios, the fragility of fossil fuel-dependent machines predicts that their complex maintenance regimes collapse without human caretakers. Yet simpler cyber-physical systems powered by renewable sources and capable of localized maintenance could persist longer. If such systems evolved mechanisms for extracting energy, solar arrays that self-clean via simple mechanisms, wind turbines that hibernate and restart, or microbial fuel cells in sediments, they might continue to influence local ecosystems, creating hybrid habitats where technology and biology co-evolve. The geological signature of such a technosphere could be unique, concentrated alloys in sediments, persistent magnetic anomalies from data storage materials, or layers rich in composite materials with no natural analog. Whether these features constitute life is a conceptual debate. They would, however, be legible as intentional artifacts that shaped their environments long after humans faded. Cephalopods and corvids often enter speculative conversations about future intelligence. Their current cognitive complexity, problem-solving, social learning, tool use makes them plausible candidates, in principle, for further cognitive elaboration, yet evolutionary plausibility is constrained by many factors: reproductive rates, population sizes, ecological buffering, and anatomical possibilities for manipulative abilities. Intelligence that leads to planetary reshaping requires not only complex minds, but bodies capable of manipulating distant and massive energy flows, communities able to transmit innovations across generations, and social systems that scale cooperation beyond kin networks. The fossil record offers caution. High encephalization alone does not ensure environmental dominance. Evolutionary paths are not teleological, they are contingent. A clever octopus living in a reef cannot easily invent metallurgy if its world lacks the sediments and social scaffolding to accumulate and transmit the necessary practices. Still, the possibility invites reflection. Intelligence can emerge repeatedly where ecological stability, sociality, and material affordances converge. The form it takes will be shaped by the legacies humans leave: altered climates, redistributed minerals, new niches carved by plastics, and altered hydrology. All of these successor scenarios have a shared constraint: detection. Geological processes are prodigious erasers. Plate tectonics buries heats and recycles crustal matter. Chemical weathering dissolves subtle patterns. Biological turnover rewrites communities. What persists are either chemical anomalies, ratios of isotopes, concentrations of trace elements, or exceptionally robust materials that resist diagenesis. Thus, even if a new intelligence arose and built durable structures, the odds that those artifacts would be recognizable without contextual knowledge are slim after tens of millions of years. Conversely, global-scale chemical shifts, elevated carbon dioxide, altered nitrogen signatures from fertilizer use, pervasive synthetic polymers are more likely to remain. In short, the planet's library records processes more faithfully than stories. It favors chemistry and morphology over narrative and meaning. Beyond physical constraints, there is a psychological and ethical dimension. The prospect that humans might be a stage can engender terror, liberation, humility, or resolve. For some, it constricts purpose. If human achievements will be geologically invisible, what accounts for meaning? For others, it is liberating. Transience frees urgency towards stewardship rather than immortality. The historians and the geologists' humbling overlap here. Human cultures have woven narratives of destiny, apocalypse, and continuity. Accepting ephemerality does not strip those narratives of value, it reframes them. If human stewardship is finite, then the moral horizon becomes not merely the next generation, but the planetary archive, a set of choices about what to leave in the strata: toxins, plastics, and isotopic scars, or preserved seeds, durable cultural repositories, and landscapes managed for resilience. The question of successor life is therefore not merely speculative biology, it is a prompt for responsibility. There is another, subtler possibility: humans could intentionally design their successors. The capacity for foresight, for technological planning, and for cultural transmission means that a species can shape the adaptive landscape in ways beyond the slowly grinding hand of natural selection. Seed banks, genetic libraries, habitat engineering, and intentional de-extinction projects are early instances of such agency. A deliberate intervention might seek to craft lineages, biological or machine, that inherit human knowledge and values. That project raises moral dilemmas. Who decides what values are encoded, what life forms are warranted, and how to anticipate unintended ecological cascades? Moreover, intentional design does not guarantee persistence. It merely relocates contingency to the track of human choices. A designed successor might fail spectacularly, or it might thrive. The audacity of design makes the question ethical as well as technical. If the successor is probable, what does that mean for human self-understanding? It reframes species-level hubris as a temporal miscalculation. The narrative of inevitable ascent, that life culminates in a single species with an exclusive claim to meaning, is an artifact of human cognition, not a cosmic law. Evolutionary history suggests cycles of ascent and decline, driven by contingencies and thresholds. Seeing oneself as a stage invites different metaphors: humans as gardeners of a long-lived garden, as participants in a relay where the baton will one day pass, or as temporary custodians of a system whose continuities do not require human memory to persist. There is, finally, the intimacy of imagination. The mind that projects successors is also the mind capable of making different choices today. Speculation about post-human forms is not merely idle curiosity, it is a reflective tool. It sharpens awareness that current alterations, climate disruption, mass extinctions, landscape engineering are modifications of the scaffolding that any future life will inherit. The futures that unfold depend on the choices that compress into the present, whether to conserve, to repair, to design, or to exploit. In the end, the idea that humans might be a phase is both an answer and a question. It answers the empirical observation of deep time. Dominance is transient. It asks an ethical and existential question that belongs to the present moment. What kind of stage will humans prepare for the next actors? The planet will, as it always has, carry on, microbial, wooded, reefed, rocky, improvising new arrangements from residues of old. Whether those arrangements include new intelligences, engineered descendants, or simply a microbial rebalancing, the narrative will continue. The lasting choice is not whether humans are temporary, that is already likely, but what traces of intention, care, and wisdom are left in the sediment of their departure. What, exactly, will remain when the loud chorus of human life quiets? That question is neither purely sentimental nor only forensic. It sits between the two, a hinge that opens onto timescales where the familiar becomes foreign. The list of human legacies, radio waves, nuclear waste, artificial satellites, plastics, altered isotopic ratios, scarred landscapes is short and specific in form, but vast in implication. Each is an imprint of intention, a kind of signature the species has been leaving on its planet and the near space around it. Together they form a book of strange rubbings and marginalia, sometimes obvious, sometimes faint, often chemical rather than pictorial. The essential puzzles whether any distant reader, an alien, a far future geologist, or a later evolving intelligence, could decode that book and read the cultures that wrote it. Radio is the most literal whisper humanity cast into space. For nearly a century, the planet has been broadcasting a fecund, chaotic flood of radio frequency energy, music, news, radar pulses, and the chatter of satellites. These signals move at light speed and spill out into the cosmic ocean like concentric ripples. For a neighbor star 20 light years away, the 1930s still play in the background today. But the physical reality of radio propagation is harsh. Unmodulated continuous wave radar is bright locally but fades with distance according to the inverse square law by the time. Ubiquitous broadcast leakage reaches interstellar distances. It is faint drowned by the sun's radio noise, by cosmic microwave background, and by the natural radio emissions of planets and stars. The detectability of Earth's unintentional radio leakage depends on power, frequency, and duration. High-power, narrow-band transmissions, military radars, planetary radars used to map asteroids are easier to detect at great distance than the background hiss of AM/FM stations. A deliberate, beamed transmission could be visible across interstellar scales. Casual leakage is not. Even within the solar neighborhood, radio signals are ephemeral. The ionosphere and solar storms scramble and scatter transmissions. After travel through interstellar space, any remaining coherence is smeared by dispersion. In practice, the window where Earth's accidental radial voice is both strong and novel is short, decades to a few centuries. A civilization attentive and equipped to sift narrow, temporally precise signals might detect the tail of human leakage for a limited time. After that, the whisper sinks below thresholds of detection. The lesson, then, is blunt. Unless signals were intentionally beamed outward, radio is a transitory monument, spectacularly useful while it exists, but unlikely to persist as legible evidence across millions of years. Nuclear technology is different. It has scarred continents with a different kind of permanence because it left behind an element of time itself, isotopes with long half-lives. Atmospheric nuclear tests in the mid-20th century spewed radionuclides across the globe. Traces of plutonium isotopes, cesium-137, and other fallout were sequestered in soils, ice cores, and ocean sediments. Some isotopes decay within decades, others remain for hundreds of millennia. Plutonium-239, for instance, has a half-life of 24,100 years. Traces of anthropogenic plutonium and certain man-made isotopic ratios are detectable in the geologic record and serve as a nearly global, synchronous horizon, a timestamp that future sedimentologists would find unambiguous. A planet's strata marked by a thin layer of anomalous radionuclides argues strongly for an industrial actor that once manipulated nuclear processes. Beyond tests lies the problem of waste, spent fuel, and high-level radioactive repositories. Engineered containment is designed to endure centuries to millennia, but geologic timescales are vast and indifferent. Strategies that seem permanent in human institutional terms, concrete vaults, deep repositories cut into stable bedrock exist within a matrix of tectonics, erosion, and hydrogeology that will slowly rework them. Leaching can transport radionuclides into groundwater. Chemical alteration can produce secondary minerals that move isotopes into unexpected places. Still, compared to the brief lifespan of radio leakage, nuclear isotopes are stubborn. They do not require human maintenance to be legible. They merely require that someone look with the right instruments. In that sense, nuclear activity is one of the most durable fingerprints humanity could leave. Satellites orbiting Earth are a third immediate legacy. For decades, humanity has populated near-Earth space with functioning satellites, defunct platforms, and debris. Low Earth orbit, LEO, is crowded and transient. Atmospheric drag ensures that many small satellites decay over decades or centuries, burning in the atmosphere and leaving only specks of melted metal. Higher orbits, however, are different. Geostationary belts and certain graveyard orbits can retain objects for tens of thousands of years. The Moon, being gravitationally stable and airless, is an even more durable archive. Apollo flags, suits, rovers, and discarded instruments sit on a surface where there is neither wind, water, nor biological activity to erode them. Footprints and tool marks may persist for millions of years unless impacted by micrometeoroids or buried by the slow gardening of regolith. In cosmic terms, lunar artifacts offer a distinct kind of legibility, a human-made presence preserved on a body that does not recycle its surface. On Earth, satellites create a transient ring and a particulate legacy. Space debris re-enters and distributes rare alloys and composites across the planet's surface. Atmospheric ablation spreads small fragments. Larger pieces can survive to impact and leave concentrated anomalies in local sediments. Human-made radioactive isotopes have also been deposited on lunar regolith by fallout and nuclear-pumped experiments, soldering our chemical signature to another world. The visibility of artificial objects in space to distant observers, though, is constrained by the same physics that limits radio: brightness dilution. A decade's worth of communication satellites would be invisible to a probe passing a distant star, but the Moon's artifacts may be detectable from a craft visiting the Earth-Moon system. Then there are the earthbound residues that pervade the crust: plastics, concrete, alloys, and synthetic compounds. Plastics are molecular novelties in the history of life. They fragment rather than biodegrade in most environments, producing microplastics that colonize soils, sediments, and biota. Over centuries, plastics migrate with sediment, become incorporated into ocean deposits, and act as markers of a unique technogenic layer. Unlike isotopes, plastics are chemically strange in a sedimentary context, long-chain polymers embedded amidst organic and inorganic debris. In a future core sample, a layer rich in fragmented polymers would be a clear signal of an unusual chemistry at the time of deposition. Concrete is another anthropogenic rock. Vast quantities of concrete and cement have been poured worldwide. Over millennia, concrete weathers, but in certain depositional settings, particularly in coastal, deltaic, or anthropogenically sheltered basins, aggregate and cemented layers analogous to rock strata can form. Such materials differ in mineralogy and microtexture from natural carbonate or siliciclastic sediments. They are a technofossil, dense, manufactured rock with distinct chemistry and microstructures that mark a human influence on sediment budgets. Mining, quarries, and large-scale earthworks concentrate metals and leave geometrical scars on the surface. Open pit mines reorder landscapes in ways visible from space as well as from the ground. Tailings ponds leach heavy metals, altering the geochemistry of downstream sediments. In the rock record, these zones may lithify into ore bodies and mineralized sequences that deviate from natural expectations. Large-scale extraction also changes the sediment budget of rivers. Reduced sediment delivery to coasts leads to altered delta architecture. These are enduring, if often subtle, traces of an industrial appetite for raw materials. Beyond the physical objects are chemical shifts writ large. The combustion of fossil fuels has shifted the isotopic composition of atmospheric carbon. Carbon-13 to carbon-12 ratios reflect the input of ancient organic carbon into the atmosphere. Nitrogen cycles have been reworked by synthetic fertilizers, changing the ratio of nitrogen isotopes deposited in soils and sediments. Black carbon from combustion, soot from industry, microtectites from urban fires. These disperse globally as aerosols and particulate matter. In ice cores, tree rings, and marine sediments, these shifts appear as anomalous excursions, steep, rapid inflections in the slow curves that normally describe Earth's biogeochemical cycles. In a stratigraphic cross-section, the mid-20th century great acceleration is a spike, a narrow but globally distributed horizon that stands out because it is both rapid and chemically unusual. There is an important asymmetry in what is preserved and what is legible. Geological processes, subduction, metamorphism, erosion, erase much of the topmost veneer of crust within hundreds of millions of years. Plate tectonics will take slabs of continental crust and grind them into the mantle. Mountain chains rise and fall. Sediments are compressed and metamorphosed. Narrative detail, cities, libraries, ephemeral cultural forms perishes long before chemical anomalies. Isotopic excursions, dispersed radionuclides, concentrations of heavy metals, and the particulate remains of plastics are the things most likely to survive the planet's memory. The stratigraphic record prefers chemistry and pattern over story. This calculus has implications for detectability beyond Earth. A future spacefaring intelligence examining Earth from afar might not see the geometry of cities unless it had the temporal coincidence of a high-resolution, contemporaneous gaze. But a sufficiently advanced probe with spectrometers could detect the atmospheric changes that mark the Anthropocene: elevated CO2, altered methane concentrations, anomalous chlorofluorocarbons, CFCs, and other industrial gases that have no natural analog at those abundances. In principle, such signatures are detectable across interstellar distances if they are large enough and sustained. The distinction between accidental leakage and intentional beacon remains crucial. Intentional technological signatures, engineered isotopic ratios, coded megastructures, narrowly beamed continuous signals stand a far better chance of being noticed than diffuse accidental pollution. That observation folds back into ethical thinking. If radio leakage fades and chemical anomalies alone might be what future readers find, then humans have been leaving a ledger chiefly of environmental consequence rather than cultural record. Plastics, isotopic shifts, and radionuclide layers are not poetic inscriptions. They are the residuals of energy use, warfare, convenience, and industrial scale. The species capable of imagining the deep past is now faced with crafting the kind of past it will leave. That is a moral design problem: what to preserve, what to let go, and how to constrain unwanted persistence. It reframes stewardship as a question about the kinds of legacies deemed acceptable to fall into Earth's strata. There is also a pragmatic angle. Some legacies are intentionally durable. Seed banks, libraries, and distributed archives attempt to preserve knowledge. Conservation repositories and gene banks store biological information. But such repositories are themselves fragile. They require energy, maintenance, and social continuity. The physical forms most likely to be legible without human stewardship are those that change planetary chemistry or geometry: radionuclide horizons, plastic-rich sediment beds, and large-scale mineral redistribution. If the goal is to craft a long-lasting record of culture, then society must either design durable archives that do not require continuous upkeep, monuments designed to survive geological processes, or accept that the record left in the rocks will be fragmentary and interpretive. Speculation about detection invites a wider philosophical restraint. The possibility that another intelligence, visiting robots, alien geologists, or a derivative life form could read our isotopic ledger assumes that the reader has both the motive and the method to interpret. Chemical anomalies in contextual terms. Geochemical signatures do not inherently encode meaning in human categories. They are patterns to be explained. A future investigator might infer an industrial perturbation from a sudden spike in black carbon or a layer rich in synthetic polymers. But to translate those signals into a tale of politics, ethics, or art requires interpretive frameworks that are contingent on shared assumptions. That uncertainty opens another ethical horizon. If the future readers are likely to encounter chemical signatures, but not poems, then what story should those chemicals tell? A cautionary tale about extraction and waste? A careful, ordered deposition of seeds and knowledge? A mixture of both? The planet's archive will not adjudicate moral nuance. It will record that something changed, and the rest will be interpretation. The responsibility, then, is practical as well as moral. To make the geological evidence reflect values humanity might be proud to have left behind. A closing paradox endures. Humanity's creative and destructive acts are both ephemeral and stubborn. The most durable signatures are not always the most flattering. Nuclear fallout, plastic ubiquity, and altered isotopic baselines narrate power unmoored from stewardship. At the same time, the capacity to imagine such futures, indeed, the capacity to shape a different ledger, is a uniquely human power. The tools exist, the science is clear, and the options are political. Choosing to craft a legacy that favors repair, that reduces persistent pollutants, that invests in durable cultural repositories is an act of long-term thinking rare in evolutionary history. In the end, the planet will keep its record, partial as it will be. Rocks will archive isotopes, sediments will trap polymers, the moon will hold footprints. The universe, vast and indifferent, will intercept radio whispers and keep their echoes only briefly. The question is not whether any celestial reader could, in principle, decode the book humanity has begun to write. The question is which chapters humanity allows to accumulate and how the intentional marks at least will be read as a warning, as a lesson in hubris, as evidence of tender care, or as an ambiguous stain. That choice between transient noise and durable, meaningful imprint is itself the most telling legacy any species can leave. 11. Earth, the silent witness. What if the planet kept its ledger long after its scribes were gone? What if the momentary clamor that fills the age of humans is only a single, bright footnote in a manuscript that stretches back billions of pages? The idea that Earth would simply go on, indifferent to applause or grief, is at once a consoling thought and an unnerving verdict. For the planet, absence is not a problem, it is a condition to manage. The world does not require an audience to continue its processes. Earth has been conducting its affairs for eons through catastrophes far larger than any human drama, and it will continue when the human voice becomes quiet. The image that best explains this is not one of triumph but of persistence, a vast instrument whose strings are long and slow. Plate tectonics, the planet's mechanical metronome, ticks on with a slowness that mocks urgency. Mountains uplift and crumble not because anyone wills them to, but because the mantle convects and pushes. Oceans deepen and shallow as plates expand and collide. Volcanoes breathe chemical memory into the air. Rivers translate topography into sedimentary language. These are not the gestures of a being in mourning. They are the ongoing verbs of a system that predates sense and will outlast it. Consider the scale of geological operations. A mountain range can be born in a few million years and erode away over a few tens of millions. Oceans migrate across latitudes, continents stitch and rip like slow-motion fabric. The rock cycle chews and re-chews Earth's outer skin. Sediments lithify into stone, are thrust up, erode, become sediment again, and occasionally sink beneath a subduction zone where their chemistry is reincorporated into the mantle. In a time span that matters to rocks, a few thousand years is a hiccup. Civilizations are fast phenomena, bursts of radiance on a surface that slowly obliterates the traces of its own recent stories, and yet the planet remembers in specific ways. Memory for Earth is a ledger of chemistry, texture, and spatial rearrangement. It keeps isotopic notations where carbon reservoirs have been unhinged. It preserves abrupt layers of soot and black shales where oxygen temporarily failed. It stores banded iron formations as testimony to ancient chemical revolutions. These are not stories in the human sense. They are measurable changes, legible to a mind that reads ratios and microstructures instead of narratives. The planet records change rather than meaning, pattern rather than motive. The resiliency of life is part of that planetary testimony. Life has a long history of persistence, not because it clings to a particular configuration, but because it is adaptable and opportunistic. Microbes reclaim the planet after massive sterilizations, not by replicating previous ecosystems, but by inventing new ones. After mass extinctions, lineages that survived exploited vacant niches and radiated into forms that were unpredictable and novel. Extinction is not an ending so much as a reshuffle. The biosphere reconstitutes itself under new initial conditions. That process is indifferent to memory and deeply creative. This indifference has an emotional contour that is difficult to hold. On the one hand, there is comfort in the planet's refusal to require an audience. Life will continue, in some form, to weave complexity. On the other hand, that continuation dissolves human sentimental attachments. The monuments erected for identity and meaning, plazas, libraries, digital networks full of intimate histories, are transitory things on a planetary scale. Stone erodes, archives decay, servers fail. The planet's persistence invites a humbled awe. Earth is not impoverished by the loss of human stories. It is simply inexorable. Yet saying the planet does not need humans should not be a detachment from ethical consequence. The same processes that permit the planet to endure also mean that human interventions have long echoes. If Earth can remold itself, it can also record the fingerprints of those who acted upon it. Chemical signatures, anomalies in stratigraphy, concentrations of metals, the expanded horizons of plastics, the radionuclide markers from nuclear tests. These are durable. They are the archive humanity is most likely to leave. The planet will thus be both silent and articulate, quiet on the matter of intent, noisy on the matter of effect. What would Earth look like, materially, after humanity is no longer in the picture? Ecological succession will begin where maintenance stops. Urban infrastructures, roads, pipes, buildings will first wear, then fail, then be co-opted. Vegetation will exploit the microhabitats created by decay. Lichens and mosses colonize facades, shoots force apart mortar, roots pry at foundations. Within decades, the geometry of human planning will soften into the randomness of succession. Within centuries, forests can reoccupy cultivated valleys, rivers will rescope channels where channelization has failed, wetlands will re-emerge where drainage systems lapse. The visible choreography is rapid in human terms, but modest in geological measure. Beneath the visible, the less obvious record persists. Chemical alterations in soils and sediments, elevated nitrogen from synthetic fertilizers, phosphorus lodged in river deltas, microplastics embedded in marine sediments will fossilize as stratigraphic oddities. The radionuclide horizon of the mid-20th century will remain a clear, datable marker across a vast range of depositional settings. Coal seams and glacial deposits tell long stories across epochs. Now they will bear the strange chapter of industrial combustion. In the long run, these chemical and textural signatures are the planet's footnotes about a species that altered atmospheric chemistry and redistributed materials at scale. The planet is also generous in its rebuilding, where human influence has created new niches. Farms and pastures, urban heat islands, reservoirs and canals, life will colonize and adapt. Some species will decline, others will flourish. Domesticated animals may go feral and become new lineages molded by selection pressures without human mediation. Microbial communities that metabolize synthetic compounds are likely to diversify in response to the barrage of novel substrates humanity introduced. Evolution is not teleological, it is opportunistic. The forms that arise will speak to the altered initial conditions, not to the intentions that created those conditions. Looking much further ahead, geology reduces detail but keeps signature. Plate tectonics will bury and rework surfaces, sediments will lithify, be uplifted, eroded, and recycled. Over tens to hundreds of millions of years, most recognizable structures of human civilization, roads, skyscrapers, cities, will be ground down, dispersed, and reincorporated into new rocks. The most persistent testimony will be chemical and mineralogical anomalies, stratigraphic layers rich in novel compounds, isotopic excursions, and lithified anthropogenic materials that do not fit the natural catalog. The imprint of humans on the planet's memory is less pictorial and more chemical, legible to a mind trained in isotopes rather than to one searching for monuments. This realization yields a paradox of responsibility. If the things most likely to endure are the chemical consequences of extraction and pollution, then the geological record the future readers find will tell a story of consumption and waste unless other choices are made. The ethics of stewardship, therefore, is not merely sentimental, it is forensic, choosing which materials to distribute, how to manage emissions, what legacies to codify in durable archives. These are acts of curation for a book that will be read by whatever attention reaches through time. To leave a stratigraphic record that testifies to care rather than to exploitation is a deliberate cultural decision. The planet's silence is also a witness to scale. When the great volcanic provinces erupted or when bolides struck, Earth experienced global perturbations so large that entire biotas reorganized. Those events dwarf the fastest of human-made changes in energy release, but not necessarily in rate of chemical change. The Paleocene-Eocene thermal maximum and the largest flood basalts unfolded over timescales that allowed certain feedbacks to operate. The Anthropocene presents a different challenge because of the velocity of change, which can outrun the adaptive capacities of many systems. In this difference lies the urgency. Earth will continue without humans, but the path it takes may be one of impoverishment for many current species and habitats. There is an aesthetic element to this thought. The beauty of Earth's processes is not a static beauty of landscapes, but a dynamic beauty of systems knitting themselves across time. Coral reefs, mangrove assemblies, forest succession, river meanders. These are not fixed pictures, but ongoing acts of construction and adjustment. The planet's artistry lies in resilience and recomposition, not in preservation. Recognizing this reshapes human grief. Mourning is real because much will change and many things will be lost, but grief coexists with the knowledge that life will find forms again, albeit different ones. Emotionally, the image of Earth continuing without humans invites a double posture, humility and a kind of tender responsibility. Humility, because human permanence is an illusion in the face of planetary time. Tender responsibility, because the very shortness of human tenure grants actions an unusual moral weight. The choices made by an agent capable of altering atmospheric chemistry and reshaping landscapes are consequential for epochs. A species that can query the deep past is uniquely positioned to think about the deep future. If the planet will go on, humans must decide what traces to leave behind. Part of that ethical calculus is practical, designing materials and systems that do not leave hazardous, long-lived residues, protecting living systems that provide resilience and regenerative capacity, and investing in archives that are materially durable and distributed rather than centralized and fragile. Another part is imaginative, cultivating a sense of belonging to a story larger than immediate generations. To act with a horizon of centuries, millennia or more, is to reconfigure cultural priorities, economic incentives, and political institutions, an enormous socio-technical task, but not an impossible one if framed as intentional stewardship rather than as a concession to despair. And finally, the planet's role as silent witness is itself a lesson in perspective. The Earth neither esteems nor denigrates the beings that inhabit it. It receives, records, erases, and remakes. The humility that comes from understanding this is not despair, it can be energizing. It reframes survival and meaning as acts embedded in a larger, patient choreography. The human moment, brief and luminous, can be an act of care, a deliberate inscription into the strata that names values rather than merely physics. Or it can be a rash set of chemical notes that future readers interpret as a cautionary marker. Either way, Earth will be the archive and the arbiter, silent, impartial, and enduring. In the end, the silent witness is not a neutral background, but an interlocutor of a particular kind. It does not speak in words, but in ratios and textures, in layers and mineral anomalies. It does not adjudicate moral worth, but it does adjudicate consequence. The planet keeps a patient ledger. The question is whether the chapter humans write into that ledger will be remembered as a brief outbreak of hubris, a measured stewardship experiment, or simply as one of many experiments in the long and ongoing history of a planet that never needed us to continue, but which may, through our choices, remember us differently. What if the story did not have to end with a final flourish from humankind? What if the proper posture before the Book of Earth was not triumphal closure, but a slow, considered folding of a page? The idea is as simple as it is unsettling: humility in the face of cosmic duration. In the hush after that realization, a cascade of questions follows, some forensic, some ethical, some quietly imaginative. If humans are only a chapter, what will the next chapter look like? Who will read the faint ink we leave behind? And what, precisely, is the moral work of a species that can write so loudly into the geological ledger? Humility arrives like a clearing of the throat. It is not self-abnegation for its own sake, nor is it a plea for resignation. Rather, it is a recalibration of scale and intent. To stand humbly before deep time is to acknowledge two facts simultaneously. The first is simple: the planet's processes are patient and impartial. Plate tectonics, sedimentation, the chemistry of anoxic basins. These mechanisms do not respond to human importance. They respond to mass, heat, pressure, and chemistry. The second fact is startling: humans, in a few thousand concentrated years, have acquired the ability to alter some of those very processes. The combination of those facts creates moral urgency. The planet will not attend to human drama, but it will archive consequences. A final chapter needs neither Gnostic closure nor theatrical finality. It needs thoughtfulness. The aesthetic at work here is not an elegy for a vanished protagonist, but a meditation on stewardship, and on the possible futures that follow a species' temporary dominion. Two broad directions present themselves, one forensic, one aspirational. The forensic direction asks, what traces will remain? What future geologists or alien visitors or late evolving lineages would find in the strata, and how those traces will be interpreted? The aspirational direction asks how a species that understands its fleetingness might choose to behave if it cares about what the planet remembers. Forensic answers are concrete, almost stubbornly so. The durable marks left by industry radiogenic isotopes from nuclear testing, the global layer of microplastics, the isotopic excursion and carbon ratios from fossil fuels, the concentrations of heavy metals near former mines are the kinds of anomalies that will persist. They will be easy to detect by any observer who reads chemistry rather than culture. Satellites decay, cities crumble, marble plazas and polished glass facades will weather into indistinguishable grains and be carried into river deltas or the deep sea. But isotopic ratios, technogenic polymers, and mineralogical anomalies are the planet's archives because chemistry outlives semantics. This is the sober, almost forensic truth. The planet will remember processes and patterns better than it will preserve meaning. That fact imposes a special burden. If what is most likely to survive is not story but chemistry, then the narrative humanity writes into the rock record will be judged by its geochemical honesty. Will that record testify to a species that learned restraint, reducing persistent pollutants, phasing out long-lived toxins, designing materials for circularity, or will it read in black carbon and plastic specks as the fossilized trail of convenience and extraction? This is not a purely symbolic question. It is a practical design problem. What materials, policies, and institutions can minimize the future archaeologist's condemnation and maximize the chance that future readers will find something resembling care? Choices about what to preserve are already material. Seed vaults, for example, are an attempt to hand a future narrator a vocabulary of life. Distributed archives, baked clay tablets stored within geological stability, and deep, redundant digital protocols are attempts to create reading rooms that do not depend on continuous human maintenance. Planting forests, protecting wetlands, and restoring soils are actions aiming to shape the ecological substrate that will persist, an attempt to alter the next paragraph's opening lines in favor of resilience rather than decline. Even choices about where to place repositories on tectonically stable cratons rather than on river deltas are acts of geological prudence. These are not gestures of vanity. They are pragmatic investments in transmissibility across time. But the humility demanded by the Book of Earth is more than a set of preservation techniques. It is an ethical stance about the kind of pressure humanity will put on planetary systems while it persists. That stance recognizes that intervention can be both creative and destructive. Controlled intervention reforestation that follows ecological principles, urban design that reduces fragmentation, agricultural systems that prioritize soil carbon and biodiversity can be a craft of long-term care. Reckless intervention, short-term extraction, economies that externalize ecological costs, the steady release of persistent compounds writes a different, less flattering stratigraphic story. The question before any demanding moral imagination is whether stewardship can be institutionalized at scales that match the physical processes under threat. Institutionalizing stewardship is not merely the work of engineers and policymakers. It is cultural work, a reconfiguration of storytelling so that the future matters in the present. To imagine policies that value centuries, humans must develop civic languages that make centuries palpable, rituals that bind grandchildren and great-grandchildren into responsibility, legal structures that translate long-term impacts into current liabilities, economic incentives that discount the immediate but fund the durable. It is difficult work because the mechanisms that translate individual actions into geochemical change are often diffuse and delayed. Yet that difficulty does not make the responsibility vanish. Instead, it reframes the civic imagination. To govern well across deep time means to create durable, redundant systems that are robust to the frictions of politics and the vicissitudes of resources. Speculation about successes, the rehearsals of life that will follow a human chapter, must also be rooted in humility. The planet does not plan, it rearranges. Given the residues humans deposit, novel polymers, altered nutrient fluxes, new metal concentrations, future biotic assemblages will evolve in response. Microbes will almost certainly lead that evolution. Already, some bacteria metabolize plastic and hydrocarbons given time. Selection will refine such pathways into communities that dominate polluted sediments. Far from being a bleak vision, this is also a biological possibility of creativity. Life innovates with whatever substrates are available. The successes might be microbial consortia knitting new biochemical cycles, feral descendants of domesticated animals carving niches among ruins, or, less likely but conceptually possible, technologic remnants that persist long enough to influence nascent ecologies. That last possibility, machines outlasting their makers, carries a special set of constraints. Machines require energy, materials, and maintenance. A self-maintaining technosphere would need local energy flows, repair systems, and autonomy conditions that are difficult to sustain without extensive infrastructural ecosystems. Still, simpler cyber-physical artifacts, minimal solar arrays, self-regulating environmental monitors, or passive instruments left intentionally in stable contexts could persist longer than much that is ephemeral. If humans choose to leave durable, non-biological artifacts, those artifacts would be legible as intentionality in the geological record. The ethical question then becomes, what should be left behind intentionally? A library of art woven into ceramic stelae? A global seed repository? An ensemble of planetary warning markers? The answers require not only technical competence, but civic imagination and humility. Humility also requires recognizing the limits of detection and interpretation. A future intelligence reading rock layers will see signatures, but interpretive context will be impoverished. Chemical excursions will be visible, the motivations behind them obscure. The moral implication is twofold. First, humanity should not seek immortal fame as a substitute for ethical action. Longevity in the fossil record is not equivalent to moral worth. Second, if a species cares about being understood by the far future, it must design messages that translate across cognitive boundaries, messages encoded in materials and forms that survive and that are legible to beings unfamiliar with human semiotics. Monumentality for its own sake is a fragile pursuit. Insulation of meaning requires humility about transmissibility. The emotional register that threads through this conclusion is not a single chord but a complex harmony, grief interleaved with wonder, anxiety braided with the possibility of redemption. Grief is appropriate because many beloved entities, species, ecosystems, cultures are fragile on the scale of human influence. Wonder is also appropriate. The achievement of consciousness able to form these questions, to map isotopic excursions, to model climate feedbacks and to design materials is itself remarkable. Anxiety is the correct political sentiment when confronted with impending threshold effects, warming beyond adaptation, ice sheets unraveling, soils compacted and eroded. Yet redemption exists as a practical possibility, mitigation, repair, and intentional legibility. The bittersweet truth is that humility does not preclude hope, it disciplines it. That discipline has practical contours. One is triage, identifying what is uniquely precious and irrecoverable, the tips of biodiversity, cultural repositories that are not easily reconstructed, and investing disproportionately in their protection. A second is repair at scale, restoring peatlands, investing in carbon removal where it has co-benefits for ecosystems, rebuilding ecological connectivity to allow species migration in changing climates. A third is design with end of life in mind, materials engineered for circularity, plastics that break down into innocuous byproducts, urban fabrics that are adaptable rather than brittle. A final contour is the crafting of cultural heuristics, education and rituals that make the long view a practical consideration in everyday decisions. The deeper ethical shift called for is the acceptance of modesty without paralysis. To be humble about cosmic scale is not to relinquish agency, it is to use it more wisely. It is to match capacity with restraint. The paradox is productive. A species capable of altering atmospheres bears the moral responsibility to limit harms and to create legible archives that testify to care, not only impact. What will come after humanity is not a single answer but a set of conditional scenarios. Microbial ascendancy where chemistry is the lingua franca, ecological reassembly where novel assemblages emerge from legacy, substrates, technological persistence and select durable artifacts, or deliberate human-designed legacy systems that seed future knowledge. All are possible, none is inevitable. The difference between them depends on choices made now, choices about emissions, materials, governance, and the cultivation of civic forms that value the centuries. In that sense, the final humility is aspirational. It asks for a reorientation of the present toward a horizon, that is, by definition, beyond immediate gratification. The book that Earth preserves will contain the trace of human capabilities, the geological exclamation of the Anthropocene, but it could also contain margins inscribed with care, a globally coordinated network of seed banks, durable inscriptions crafted in stable minerals, a global museum of biosafety protocols, or simply a reduced flow of persistent pollutants that allows future ecologies to reorganize with less trauma. Those margins are decisions as much as they are acts of engineering. There is a human comfort in possibility. To know that the planet will go on regardless is not to deny mourning, it is to recognize that the planet's continuance offers a canvas for repair. The humility of the cosmic view invites an ethic of curatorship rather than possession. It suggests a final, modest sentence for the human chapter, not a demand for eternal remembrance, but an offer to the future, an offer of seeds, of stories carved into durable media, of cleaner chemistry, and of landscapes, managed so that life's capacity to recombine remains robust. If the reader wishes to imagine a last image, let it be a thin, bright horizon and a geologic core, an unusual agglomeration of polymers, a spike in isotopes, and within that horizon a deliberately buried repository, a simple, redundant archive containing seeds and encoded text designed for legibility by any curious future mind that knows how to read. Chemistry and pattern. Around that repository, a rewilded landscape hums. Microbes whisper, trees root into the old city's bones, rivers smooth once rigid geometry into meanders. The record will say, in the language of elements, here was a species that could have been a catastrophe, but chose, in part, to be a steward. It will not tell the whole story. It will not record every kindness or every cruelty, but it will leave a note, an ethic written in matter rather than rhetoric. The final question returns, sonorous and open. If humans are a phase, what comes after? The answer is both tentative and potent. What comes after depends on the humility with which this phase is lived. Humility does not erase ambition. It channels ambition toward a long game. The cosmos may not grant immortality. It does accept careful work. The planet will be patient. The human task is to be worthy of that patience,